So good morning, everybody. Can you hear me? Is this live? Yeah. Right. So I have to welcome here to this Mars Express Power Challenge final event. It's something rather new for us. We're very exciting about it, and it's rather new for me as well. Although I've been here for so many years, we're going into a new era here. This is me. I'm Paolo Ferri. I'm leading the operations department here, and I've worked more than 30 years in this environment. And I can tell you about the development of our relationship between human beings and computers. When I started my career, we were at the edge of moving from a totally manual control of the spacecraft into some sort of computer-aided control. We moved into an era where computers were helping us and doing, instead of manual checks of the telemetry of the data that were coming down, they were doing checks on thresholds that we were putting in and tell us whether the threshold was passed or not. We went into more sophisticated computers over the years, and for example, one thing that we do systematically and is the backbone of our monitoring of the spacecraft is what we call command verification. We have very complex logic to check that what we tell the spacecraft has actually been correctly executed. And we have these out-of-limit checks and so on. But we have been for many years now in an era where we tell the computer what to look for and what to tell us. Recently, and I would say in the last decade, data analytics started with a group of Alessandro Donati as a sort of experiment. And but there we learned, with various experiments, we learned that we can actually revert the thing, and basically computers can tell us what to look for. And the analysis of telemetry to find out things that are unusual has started. We've had a lot of experiments and examples of tools that basically go into the telemetry and tell us there's something strange here. Then you show it to an engineer, and the engineer normally says, oh yes, I know. Yeah, but then maybe part of it he doesn't know. And this was the next step. It was actually a discovery that we can actually revert this relation between the computer aid and ourselves. In the meantime, the world of big data has started. We live now in the world of big data. There's a lot of things going on outside that deal with data analytics. And one of the big things that are realized now is the world of prediction, is the capability of predicting. So using data to predict the future. This we have not done yet. And this is what I like about this challenge here. It brings us into the new step. While we have not yet really adapted to the previous one, yeah, we're just still experimenting the previous one. I'm very excited about this because I see it happening every day in our normal life. We hear things like Amazon will deliver things to us before we've ordered them because they know that we will order them. So the power of prediction of the future in data analytics is there, and I can see this happening already now. So it's good to try and apply it to our world. So, great experiment, great idea, and I'm very happy that we had a lot of response. I read here we got 150 people or groups that actually downloaded the data, and I think we got 40 responses, which is quite a lot. And the responses were all very interesting. You will go a bit more in detail into this, and very exciting with very, very promising results. So that's from the technical point of view. From the other aspect, which is also very important, is that this experiment opens us to the outside world. Putting data available to the outside world and available to a very wide community is like putting the seed for future cooperations. Future cooperations with a world that is not necessarily linked to our still very restricted space community. And that's also what I think this experiment is about, is looking into new ways to cooperate with a very wide community and variegated community that comes from many, many different areas where a lot of things are happening that we're not necessarily aware of. So as I said, from these two aspects, I think this was a great idea. I'm very happy of you turning up here also so numerous, and I think it will be a nice event. I'm not sure who's the master. I think Red is the master of the event. I will pass it to him, and I wish you a good day in the European Space Operations Center. Enjoy the day and also the visit to our facilities. Talk to our people, and I hope to see you again in another occasion soon. Thank you.
Thank you, Paolo. So on this slide, there is the leaderboard, so the final leaderboard. And of course, this was a challenge, also a small competition, so we've got some winners. And I'm very proud to tell you that the winners are the team MMME8, who is the Institute Joseph Stefan in Slovenia. They are here present. Please come on. Come here. Come close. Yeah, you will have one. So there are 7. You have 5 of them here. Unfortunately, yeah, well, 5, yeah, you're 5. And unfortunately, 2 of them could not make it. But so they had a really nice experience and nice teamwork. We will tell about. But before going on, we wanted to thank them. And since they worked on Mars Express, maybe Luke, you can come here. Luke Lucas, who was the Mars Express flight control team member, who was with us in this competition and organizing everything with us. And maybe you can have a little thank word for them, or
so,
yeah.
Can you hear me?
No, in the microphone, because we got the live stream.
Okay.
We've got 60 people on the live stream, so yeah.
So as a general note of thanks to everybody who took part, thank you. When we started the competition, I'm not sure we really understood or even knew how many people would be interested or how many people would take part or how it would go, but the leaderboard was really interesting to see. Actually, lots of people were really interested. And it became quite a challenge and quite a competition between all of those who took part. We also looked and saw how close you got to getting better and better and better predictions, and that was also quite interesting. Sometimes it's like a line, and then there'd be a step function as to something could change. I'm not quite sure what you did in your machine learning, but suddenly your predictions improved. So all that said, thanks to everyone, but there are winners, as happens to be the case, and as a token of thanks, so you will see that I am sporting the MEX FCT jacket. It's very nice, very fashionable. And so as a token of thanks, we also have jackets for all of you guys to say thank you very much and well done and congratulations.
So, thank you. Please, yeah, go for it, because I have many. You have 2 for the missing colleagues. So now you will look like MEX flight control team members. So they will talk later. So thank you again, and we're looking forward to your presentation. So here they are, yeah. So the 2 missing members are on the left, and one before the end of the right. And that's their score. So it's a bit, well, what does it tell? Nothing much, because you need to see the data. They will go through this. But just to compare this, we've got a runner-up, who is Stefano Stefani. I hope he's here. Yeah, please come on here. So Stefano Stefani was the second. We can approach it. Yeah. So Stefano's code name Red Rock. So that was not me. My name is Red, but that was not me. So thank you for the code name try. That was cool. So your score is very close, but nevertheless you ended up second. So thank you for your efforts. And we have also a gift for you, because I think we have to reward those kind of efforts. And since you were the first on the public leaderboard, and the second on the last leaderboard, you also get the jacket.
Okay, thank you so much.
You can go back. Yeah. He will also talk later this afternoon to present his solutions. So yeah. So as I said, this is the public leaderboard where Stefanos was the first with a certain score, but we were scoring on only on some subset of the final data set to avoid reverse engineering of the solution. And the final results were calculated at the end of the challenge, and we got this. So we got a switch between the two first. So actually, I guess the winning team has a small story about this, and as Stefanos, so we'll see that later. So I'm part of the data analytics team for operation. I will leave Alessandro Donati present the team, and I'm a research fellow in machine learning here in data science for operation. So maybe Alessandro, you can come in.
Thank you, Red. Today is a really great pleasure to have you here. And I hope you have enjoyed so far this adventure, and you enjoy further taking it as a motivation for your further work in the future. Today my short talk is more focused on a little bit of history about the data analytics team for operations. And when we started at the very beginning, say more than 10 years ago, I was, in this time, I was used to talk with my management, telling them that we are rich. And then they were coming back to me and say, "What, Alex, what are you saying? We are poor, we don't have enough funding, we are always fighting for funding." I said, well, don't misunderstand. I'm not talking about we are rich in money, but we are rich in data. We have, luckily enough, a culture of data, systematically data storage, archiving, and retrieval. And so far, we are doing just a little bit. We do, at the best, limit checking, or some printing out of visual trend analysis. But we can do much, much more with that. So this was at that time an intuition. Data mining was not yet fully developed. They were starting up the so-called data warehousing, and then on top develop a bit of layer to see what can be done with these pre-organized, extracted, transformed, and loaded data into the warehousing. And we managed to have trust, confidence, and also an essential ingredient, a bit of freedom, to start doing some early prototyping and investigation. And at the same time, we had to build up a team of expertise in-house that would be the very first, I just touched the screen. I think I have to go back, yeah. And it became a sort of, let's say, startup for us, internal startup. This team was and is highly motivated, and is not only static, it's a bit dynamic. Some people are staying, some others are going. And at the moment we have these three people as a reference, Jose, Jose, and Red. But together with them, we have other young graduate trainees or trainees or PhD candidates that are working with us and supporting our activities, plus other, let's say, external activities based on the external contracts and consultancy. What were the, let's say, the motivation that and the challenges that we faced? Were basically one which was more focused on a long-term goal was autonomy. So let's get prepared through data analytics to the future, what is coming. So, and this is an example of the great algorithms that now you have implemented and managed to do a forecast on ground. In the near future, might become a sort of a model that we can upload on board and use it as a local, near real-time, stream-based forecasting. So leveraging and getting prepared to distributed decision-making. This is happening not only, and will happen when we have space exploration, moon base, or even Martian remote or asteroid missions, even with and or without men on board. This will open the way, pave the way to be able to support these missions. And so it's an enabler technology, if you like. But then, this is the future. And then the current challenge is more on resource management, on board resource management. And this is where you are focused, for instance, with this challenge. We do our best in mission control to optimize the resources, to cope with anomalies that are coming or degradation that is happening. And we care of the spacecraft because our mission is to provide to the customer, to the science community, if it is a scientific mission, or to the customers of Earth observation missions, for instance, or etc., the best, the maximum amount and the best quality of payload data, of scientific return to the mission. But this, of course, has to be, let's say, balanced with another major objective that we have in mission operations, which is taking care of the health of the spacecraft. So caring is similar, basically, if you like, to what we are doing with ourselves. We take care of being in shape, in health, and then we try to do our best at work. These are the two threads that also we keep also for the spacecraft. And what we are doing today, what you managed to do is just a contribution to optimize the limited resources on board and enable this mission, which is an old mission, but still very valuable and appreciated by the scientific community, to do a little more of science with respect to what we did so far. And so these two challenges gave us the opportunity to, let's say, to work and focus on results, which some of them have been already illustrated, some others at technical level will be more focused on the talks today. But the two aspects that I want to mention myself are more from the cultural change of mindset. So certain results, like what came out from improving the early detection of an anomaly, improving the capability to do much deeper and focus diagnostics when a failure or an anomaly has happened, has been recognized, pave the way to change of mindset. Data analytics is not only a possibility, but it's getting more and more useful for flight control engineers, for mission operations community. This is one aspect that came out. Today, we are doing a big second step, in my opinion. Sharing data, making data available, is another step that enable not only to the let's say, to the experts that are already working in the space community, but to a much wider audience to create, to work on these challenges and to create and develop new bridges that will foster the, let's say, the activity, the space community, and enrich from people, from experts, which so far didn't have the chance to work on space-related use cases. So thank you so much, and hope that you enjoy the rest of the event. And now I give the microphone to Jose Martinez. That will go a little bit more on the technical side. Thank you.
Hi, good morning. So my name is Jose Martinez, and I work in the, I'm a bit taller. I work in the group with Alessandro, and we wanted to also take the opportunity to make an introduction for people maybe are not so familiarized with what we do, and something we are working on is data access and visualization. So to provide this data that we give to you in this open competition, we need to have the data from somewhere. We had a situation where we had the data ourselves, but it was difficult to access this data. So we developed a platform that make it easy to access this data. And we also are able to visualize, and I'd like to thank Jose, is there, and is also responsible for this graphical user interface that is being used on site. Then also for the competition we run is a competition on prediction, but I wanted to give you another overview of what kind of other things we do with data analytics that are not related to prediction. So, for instance, something we do with data analytics is anomaly investigation. Whenever there is an anomaly, there is always the question, why this anomaly happened? How can I prevent it from happening again in the future? So we realized that data analytics can help us in this task and automatically find which are the potential causes that at the end we need to check, of course, with the engineers. So the data analytics cannot do magic, but can do some pre-filtering. And the flight control engineers can then check, but it's a very valuable input for them. Another thing which is developing in the last years is anomaly detection, because our spacecraft, they have around 20,000 parameters. So we provide to you for this challenge only 33, but there are like 20,000 of them. And anything can fail at any time. And in fact, we know that something in the future, especially for missions which are longer than the time that were planned, will fail eventually, but we don't know when or how or where. And this kind of techniques allows us to automatically detect and raise the awareness of engineers when something is not going as expected. Something we're working currently on is find dependencies. So we know what should happen. When something changes in one side of the satellite, something else should change somewhere else. But this knowledge is not complete, and there are many side effects that we are not aware of. So we are trying to find these kind of things automatically. We also working on data and trend visualization. Is very important because it's what gives engineers the visibility of what's happening. It's very important to understand what's going on. And of course, prediction. And prediction is what this challenge was about. And we also did some exotic things in the past. One of them is like predicting the launch delay, for instance, which is a bit more difficult. And I'm happy to have you participating in this challenge, and I'm very happy with the very good results that you achieve. I have another slide for people who maybe are not so familiar with what machine learning is. So to put a bit of context for your presentation later on, is machine learning is a collection of tools or algorithms, models, that automatically learn from data and improve with experience or improve with new data. So the idea is that there is the data that you currently have, and you have a goal, you have a question to this data. In this challenge, the question is, what will be the thermal power consumption? So you have this data, we'll build model using this data, and this model can be used on new data to predict what will be the outcome. And this is what we intend to do. Then, Red, do you want to continue? This one? Yeah.
Thank you, Jose. You have some other microphones if you want to interact. So, okay, I'm smaller. So this is the slide to present you introduce you the challenge shortly. Who of you have participated in the challenge? So we see the candidates in the room here. Okay, okay. Your hands were catched by this camera. It's on live stream. And who of you have read the challenge and got interested in that? But the candidates. Okay, cool. So we had a platform called Kelvin's, developed by the ACT in ESTEC, and we had this challenge from April to July, all included. So that was in collaboration with ACT and with the MEX flight control team, because they provided the topic and the data as well. And the challenge was to determine with better precision the thermal power consumption. So the attribute in red here, because it's important to know what's left for science, like we said already. So we had to get some context data and target data. So we have given 3 Martian years of data, and the challengers had to predict the 4th Martian year. A Martian year is 2 Earth years. So that's quite a lot, knowing that they had to predict the thermal power consumption for every hour for all those 2 years. So what is the context data we have provided? So it was split in different files. So we have the long-term data, which includes all the eclipse information. We have the solar aspect angles, so we know the attitude of the spacecraft with respect to the sun. We have the detailed mission plans, so candidates knew what command were launched and triggered on the spacecraft, but they didn't know what the command were meaning, so they had to guess that through the data. And we had a flight dynamics timeline and event file with some redundant events on these, but there were supplementary information that could be useful, and we'll see that with the others. And then they had to predict 33 electric current lines. So from the thermal subsystem. That's a lot. That's a lot, because usually we predict only one parameter, but algorithm can do that. So we provided, from the context data, we provided 4 years, and from the target data, we only provided 3 Martian years, and they had to predict the last one here, using the context data they had on this one. So they made the link between the context and what was happening in the spacecraft, which was quite impressive. So this is a competition, so we had to get people involved, and we had to do something for that. So it's all about engaging human beings and interested minds. And we had more than 600 downloads from the website. Unfortunately, we don't know who exactly, but we know we had 133 registered candidates. Out of them, 40 were very active, 40 teams. So you see the winners were 7, so it involves more people, and many countries, of course, as you can see on the map. But what's important when you try to communicate about these challenges is to select your channels. So we had the support of ESOC communication, and that was very nice because we had a lot of views thanks to them. And they had also Facebook and Twitter. We were using those channels as well. That was quite effective. Then we used Reddit. Some people directly connected through Reddit. There's a channel, Machine Learning, on Reddit, which is quite active. And LinkedIn as well. So you have less people viewing referred by LinkedIn, but they're very engaged somehow. And I must say, The best channel ever is the meetup. So you meet the people, and you talk like here today to a group of people, then you can have a chat and a beer at the end. And so we understand better each other, we explain the challenge in more details, so people get engaged somehow. And it was very nice to meet everybody, to meet the experts. We even met some Kaggle winners, if people knows what Kaggle is. It's a machine learning website, a machine learning competition website, very famous. So we have our Kelvin's platform on which we can do more challenges. At the moment, the Max Power challenge is over, and there is another ongoing challenge, which is not a machine learning challenge. Well, it could be, but it's an algorithm challenge where you have to be the most optimized and performant. And just to have one more information is we had communicated before the event. So when we opened the door of the event, we had after the kickoff, the first submission, 36 hours and 20 minutes. That was quite impressive. And that was not so bad. This RMSE is about the baseline of the average model somehow. So that was quite motivating for us, so seeing that people were engaged right from the beginning. So we had to prepare the data. I don't know, most of you, I mean, the candidates, I've seen most of you, so you know that was a hard jump for me, but we have some other people from ESOC here. I wanted to tell you that was quite a challenge because Mars Express is quite old, and Lucas can tell as well. We spent hours trying to select the right files. So first we had to find the data files. So Luke, thank you for this. And then we had to select the files because I mean, the versioning system is what it is, and it changes over time, so we have to cope with this. Then we had to check the files, to check the quality of the files, to transform them into something readable for you, and then output the checking, so check the output. So that's an example where you see here a block of text which represent 2 lines on the right. So that was the original file on the right, so the raw file that was transformed into what is here, I believe, the FTL or something like this. So so that was quite. The important thing is that you have to know if you want to prepare a challenge yourself, because some of people here, colleagues here, wanted to do a challenge. You have to consider this took 3 months for us. But maybe it will be easier from now. So of course, when you make a challenge, you take a look at the scores. So this graph, 1 point on this graph is a submission, and so on the axis you have the time, and here on the y-axis you have the RMSE score, which is the root mean square error score. So if it's up, it's very bad, and if it's down here to 0, it's perfect. So we had those points, and I'm hearing you're laughing because yeah, this is your first submission. So so the winner's actual first submission was the worst. Okay, but I mean, so you can see that the worst, but also they started very late. So that's why the name is MMMEA, it's like a Monday morning meeting. And they spend months with meetings, as they told us yesterday. And finally started to, you know, do the job, to work, to work like the professors say. So I had to get rid of everything above 1 or 2 to see the magic in the scores. So you can see 3 big groups. It always goes like up and down, and up and down. But what's interesting is that, yeah, okay, we started various presentations before the meetup, the challenge, and even in London. So one of the first contribution were from London, and then we had different events like here, the 19th of April. We had the first submission lower than 0.10. So after that, it's the blackout somehow, because people were like, oh no, we cannot do better. somehow I got the feeling something happened like that. But then we had a meetup here with a meetup guy who should be here. Eldar, are you here? Eldar, maybe not here. Okay, Wolfgang, you're here as well. So the FFM Analytics meetup, where we met some Kaggle winners, serial winners, we say. Alex, you can raise the hand, maybe. Yeah. So, and then that got them thinking, so you need some time to get it on, certainly. And some people were submitting files. Then we had a very interesting meetup with the flight control team. So we had Jonathan Schulster, who cannot be here today, and Luke Lucas, who organized with us. And after that, you have quite a heavy density of points because Luke Lucas took great care to explain what was happening and what was the stake of the challenge and what was happening in the thermal subsystem. And then in July, that was the hackathon organized by Sebastian Appel, who is not here right now, but he will try to come today. And you can see that after this, you have a great density of submissions and also different use of algorithms, because I think some of you tried neural networks while they were not using that. So, and everything got down lower than 0.08, which was quite impressive. 0.09, sorry, then the last one with the winners, 0.08. So, which is interesting here is that we had a starter kit from Alex Bauer, and we could see that it helped a bit here people to get lower than 0.10 because people were trying to use that, and that helped also because the density of point before that is quite low, and so we know now by experience that having a starter kit with a challenge is very, very useful. So this is the 4th year. It's in green, and in blue you have the winning prediction. So that's the prediction of MMME8 team from Slovenia, and you could see that right from the beginning it's really, you have a nice fit, and then you start to deviate a bit, but it comes back again and again. And the very interesting part is here, where Luke, maybe you could talk about that, but we had some data gaps, but the predictions continued to tell what would have been the power consumption if all the commands were executed. So that's quite impressive for us, and I will show you different outcomes and how we can compare this to the current model. So one of the nice outcomes is with this we can support mission planning. So flight controllers can know, and flight operators can know when they can do more science, possibly. And we have interesting use cases for education. By discussing with the candidates, realized that some of you were using that for education, and that was very useful. So what we're going to do is to release the 4th year bit by bit, so you have a new challenge for your students all the time. And also we can also interact with you and get to spin in technologies, spin off things. That's how it could be. And then we had a great connection with a nice community of experts and enthusiasts, and that's really motivating. So thank you for that. And of course, many other benefits I won't list here. I would just want to compare the model you have, Luke, and yeah, okay, I'm sorry, I didn't show her this slide before. Yeah, that's okay. You're using just few features for your model, so that's normal. So this is the lower the better, of course. So the best RMSE is far away from your model, but to get an eye on this is the real measurement of the power consumption. It's reduced to the model, so it means that you have only 1 point per day, so it has been averaged. And in red, you have the model from the flight control team, the model they use. It's not so bad. It's not so bad, considering the RMSE we saw. And in green, we have the prediction. It doesn't look like it's very good, because it's an average per day, and we don't see the details of how it behaves. So I'm going to zoom in the October part, which is the third last point, because we have the red model, which is above the reality, and the prediction, which looks like it's under. So just a reminder. So here I have, on the top, I have the red point from the Mars Express team. At the bottom, I have the green point from the prediction, and in the middle, you have some blue points. It looks like a bit random, but if you draw the lines, you can see that the prediction is matching the behavior of what's really happening, and that's really important. So you know when you got to get peaks and things like that in your power consumption, even though they're not really precise. And the other thing is that the MEX model is per day, but we got a prediction per hour. So we got the behavior per hour, and we can see that the green line fits the behavior of the reality. So that's another great outcome that we've discovered during this competition. So I will stop talking now, because I have to leave. The mic to the winners and other candidates. But first, I would like to thank the Advanced Concept team in Nestec. So Dario Izzo and Jörg Müller, who worked hard on the platform, and their boss, Leopold Sommer, who were very supportful during website takedowns somehow. And of course, the flight control team, so James Godfrey, who is the executive SOM, and Luc Lucas, who most of you know, and Jonathan Schulster, who's working at EUMETSAT now. He was ESOC at the time, and Armel Hubo, who presented the Rosetta model yesterday to the winners. So we got inside the Rosetta facility, and that was very nice. So which is very nice that Rosetta resemble it's the mothership of MEX. So MEX is kind of a copy of Rosetta. And Roberto Palmari, who was taking the pictures. And of course, all the communication teams who are here today also, and without who we could not do this live stream. And Shahzad Hosseini, who we had discussions in the beginning to know how she managed to organize the Moon Challenge. Then the Meetup activists. So we have the Data Science Lab in London with Rebecca Way and Andrew Brooks. They're very helpful in communicating about the event. The FFM Analytics group with Eldar Rakhmatullah, I hope I'm not pronouncing it wrong, and Wolfgang Weist as well, who is here today with us, who's organizing the TEDx in the area. So that's quite interesting. And a special thank to Sebastian Appel, who is not here because he works in the shadow, so he's never here. But actually, I got to learn that he did a lot. He did a lot in the backstage, and I really thank him for that. And he also was the guy who organized the hackathon, and so that was great to see the momentum we were getting, because we were answering the question on the discussion forum, and then the candidates started to answer instead of us. So we were like just perfect. And then Sebastian Appel organized this hackathon between candidates. We did not attend, but that was a great thing, and that was very nice. And of course, thanks to special candidates like Alexander Bauer, who shared his code right from the beginning. Of course, some of you also shared the code, so thank you for this. And to Keith Trunka, who's going to record this. I think right now he's sleeping because he's in Seattle, and he was a guy using recurrent neural networks, and I'm thankful for this because that was quite a different approach, and he had lots of discussion with everybody. That was very cool. And of course, for the momentum, thank you everybody. So now Luke.
bring things up on purpose. Andy Johnson just leaving at the back. Alex has Lars, and Simon had these bits of kit just here. So the guys who ran away quickly and are now sitting at the back are part of my team, so that's why I asked them to bring things up to the front. We have Alex, Andy, Simon, and James is sitting in amongst the rest of you there. We will get round to using props later.
So if you want to...
I'm
okay,
sure
fine.
this works. So,
Yeah. Sorry. It's better?
I'm still short. So, good morning to one and all. As Red said, I am Luke Lucas and I'm part of the Mars Express Flight Control Team. I am particularly responsible for the thermal subsystem. So, first of all, thanks to Paolo this morning, so you know where you are. You're at ESOC. Who we are is the Mars Express Flight Control Team, and what we do is, literally it's in the title, we fly the spacecraft. There are many different aspects to a spacecraft, from build and test and launch, but after all that, then it's given to us, and we fly it, and we try and get the most science and the best results out of it that we can. Yes. And then there's a question of why we do this, and this picture I like, so this is why we do it. So as human beings, we've always explored, and this is what we explore, and this is where we go. This is what Mars looks like, and this is from our HRSC instrument, so this is what we do. Or what we do enables this to be possible. Yeah. So why have we got a challenge? Let me go back to that. It is a thermal challenge, and it's about thermal power. And some of you may be thinking, I don't know how many of you are interested in space or know about spacecraft, so my presentation sort of covers the basics and the overview, so you have a context and an understanding of what it is. You may be thinking, why thermal and why thermal power? Is it that difficult? You all live in houses, you all have a thermal system at home. It gets cold, the heating comes on. It gets warm, the heating goes off. Surely it should be that simple. Not exactly. So the blue line that you see is the predicted thermal power consumption over the course of 10 years, thereabouts. And so you see, it is not a flat line. It is not particularly easy to understand initially what is going on. It is quite, it's not chaotic, but it's very different. And the red line, the red dots that you see are what power was actually used compared to what we predicted in the blue line. And this is over the course of 7 years. I will talk about the other lines that you can see there as well. So, what are the factors? Why is it so difficult? What is influencing the spacecraft? What's going on with the spacecraft? What is it under the influence of that is causing this weird thermal pattern? So firstly, it is the distance of Mars Express to the Sun, which is reasonably understandable. The closer you are, the more radiation and flux you get from the Sun, so the warmer the spacecraft will be, and the further away, then the less. And so this graph shows that the distance varies between 200 and 250 million kilometers from the Sun. And in terms of what does that actually mean, this is the power difference. Yes, we go from over 700 watts per square meter, which is how it's measured, to under 500. When you have a body in space which is receiving a lot of energy or not so much energy, this makes a significant difference. And of course, the energy that's not provided from the Sun is energy that our thermal system will have to provide instead. Yep. Other things that can make an influence is, this graph gets more and more, is where we are in relation to the Sun and Earth, for which I need a fabulous assistant. So the orange line, for those who can see the orange line, that is, down here. The pink line is the distance. The orange line is more to do with how things are lined up. Yeah. You laugh, but honestly, it works. So are we in? Yeah. This is where we should be. I know it looks simple, but for the number of arguments and discussions that we have, this just resolves it all. So here we have the Sun, and here we have Earth, and here we have Mars. And Mars Express is obviously orbiting. As you know, the Sun doesn't move around the Earth moves around, so. And this is what happens over time. And we end up in this position. And when we're trying to communicate with our spacecraft around Mars, there's this whacking great big Sun in the way. And this means that we cannot communicate with the spacecraft. We cannot reliably command the spacecraft. So we set it into this sort of a basic mode where the spacecraft is happy and healthy and fine, but we are not doing any communications, we are not doing any science, we're not doing any of the things that would otherwise engage the spacecraft and keep it warm. So during this phase, the spacecraft is also quite cold. Yeah, so it is still receiving it's not to do with the influence of the sun, it's more to do with what we're doing with the spacecraft at that time. Is that clear to everyone? Yeah. My many thanks. So here I have a wee video. Hold on just a minute, because you may be wondering, when we have this conjunction, as it's called, we fly the spacecraft in a particular orientation and attitude, and can that really make such a difference? But I wanted you to see how maneuverable our spacecraft is. So, so for some reason, everything is flickering, but I hope this will work. And this is how maneuverable our spacecraft can be. And depending on which side is facing the sun or not, you'll then see, this is it in slow-mo, depending on which side is facing the sun, how much influence the sun has on particular regions. And this in turn influences how hot or how cold the spacecraft is, and then in turn how much power we have to give to the thermal system in order to keep the spacecraft operating within its good operational range. So there's that one. Dun, dun, dun. Oops. So, what else influences it? So here we have a diagram of, so we know about the distance from the sun, we know about the operations that the spacecraft might be doing, in particular in conjunction, what happens then. Also, the planet itself has an influence on the spacecraft. So all bodies have an albedo, which is how much the sun is reflected off the body. And when we're much closer to Mars, then the Mars Express receives some of this albedo flux. So this also has an influence. So now we've got the distance, the conjunction or not, and the closeness to the planet. And then finally after that, once we're going around the planet, we also have to take into account eclipses and eclipse seasons. And this is the same graph again, but we just keep on adding layers. The blue line that you see down here is the eclipse, or the eclipse season, rather. And an eclipse season can be very short, or it can be 6 months long. And during eclipse seasons, the spacecraft goes behind Mars, is in the shadow for some period of time, and receives it. Obviously, once something is in the shadow, it cools down. And so this is the eclipse in a simple format. Our spacecraft is flying around Mars. We get to the penumbra start. It goes into shadow. And during the shadow period, obviously, once we're in shadow, the solar rays are not producing any power. They can't. And at this point, we're relying purely and solely upon battery power. That is the only thing that gets us through the eclipse. Oops. And then we come out on the other side, and we're back into sunlight. And an eclipse happens every orbit, and we have an eclipse season that can last several months. So throughout that period, we have to be very careful with what we do with our power. That is the nub of this whole thing, is that eclipses are based purely on, we only have the battery power, and our batteries are degrading. They're 12, 13 years old now, and they're lithium ion, much the same as yours in a phone. There's only so much you can do with them. So, yes, here are the batteries that we have. It's important to know that MEX is very special for many, many reasons, one of them being that MEX is the first spacecraft to be using lithium-ion batteries in space for scientific purposes. And this was back in 2003, and at that time it was really quite groundbreaking. Lots of stuff now, you all have lithium-ion in your phones, but this has come on after missions like ours. So we have 3 lithium-ion batteries, 1,620 watt-hours at the beginning of life. As you'll know, phone batteries and lithium-ion batteries, all batteries will decay over time. And now we have approximately half of that. So for all the science and all the things that we could do at the beginning, we now have half of the capacity. And as we go on through the mission, that capacity will continue to reduce. So now we understand sort of the context. I wanted you to see what happens on board the spacecraft, and what does the temperature do? Is it very stable, or, and this depends on which part of the spacecraft you're looking at. Where's Max? Ah, sorry. I've not got my glasses on. So, can you see? This is our spacecraft. And a six-sided cube, effectively. Instruments at the top, high-gain antenna at front, radiators for cooling parts which need to be cooled at the bottom, what was the adapter, and the arrays on either side. And on each side within the spacecraft, lots of different things are going on. And so a spacecraft as a body is not a simple thermal unit. It is not at one temperature, and the temperature that decays or stays or raises or lowers is not doing the same thing at all points. And this is just one side. This is the, I believe this is the, yes, XTX side. So this is the side where we have the transmission. All of the stuff that we use for telecommanding is on this side. It's on one of the Ys. And at this point in time, this is from earlier this year, you can sort of see what the temperature is. It goes between -12 and 16, or not in that picture. But a little bit later, this is how it looks. So we get really quite large variations in temperature in any one spot, never mind across the spacecraft, which is part of why predicting it is really quite a bit of an art. And here again, I want to show you a video. Bum, bum, bum. Is it this one? No. So, this is taken over the course of 24 hours. This is every half hour. And this is the same side. This is where the communication side is. And you can see that the temperatures at some points really get warm, and at other times really get cold. And we've got a variation here of about, I think, from -12 up to 16. So you've got a 30-degree, oops, not that one. Apologies for that. Yeah, you can have up to 30 degrees in difference over the course of one day. So with all of these things going on, you have the activities on board. You have the activities on board. You have closeness to the planet. We have closeness to the sun. And we have, depending on our whether in conjunction or not, all of this takes part into producing what we need. You think that's what's causing it to flicker? Yes. So, now we understand the thermal environment a bit and understand why it's a bit difficult. Then we come to the power management side, and this is really the nub of what you were looking at and trying to find out on each LCL. As it says, we need to balance the power demands of the platform being parts of the spacecraft such as the onboard computer, which are always on. We can't do anything about that. And the payload against the thermal demand. It's a budget. We have a power budget, and we have to be very careful how we use it, particularly in the eclipse periods. And our challenge is, or our difficulty is, that the battery power capacity is reducing over time due to degradation. This is simply a fact of life that we have to live with. Solar array power is also slightly reduced from what it ought to have been due to issues with wiring prior to launch. And the power demand will vary according to what operations we're doing. There are so many variables in this that actually finding a good and true model has been somewhat not so easy, seeing as our RMSE is 0.5, according to what you showed us. I'm slightly mortified. I didn't think it was quite that bad. So power management is getting more and more difficult. I wanted to give you an idea as to what was going on behind and where this problem came from and why we put it out as a challenge. And then the final thing is, why bother? This is why we bother. So prior to Mars Express, it was thought that was ice at the poles. It was a proposition, it was a hypothesis, and so on. We send one spacecraft there, we take an image like this, we use spectroscopy as well, and we see that there is ice on the poles. This is why we go. It's all about the science. We find, there's another video that I haven't got here, but it shows aurora around the planet as well. No one even considered that there could be aurora at Mars, but there are, and our spacecraft found it. It's all about the discovery, and it's all about the science. We only have a certain amount of power. If we know how much power we have and how much exactly is going to be used for thermal, then we can decide quite clearly how much science we can do. At the moment, there are times when I am the bad person and say, no, we do not have enough power, we do not have enough budget, we do not have enough margin that we can do all of the science that all the scientists want to do. And we have to take out observations because I am not sure that we'll have enough power to be able to do it safely. So that's why we needed you guys. So that's what it's about. Thank you very much.
So if you have some question, you can meet Luke afterwards. Yeah. So, oops. Top secret slides. Whoops. Spoiler. So now I will leave the place to the winners. So team MMME8. So I don't know if you're coming all or just you, Yuricha. So the team leader is Yuricha Levatic, and I love the micro to him.
Yeah, Jurica. a bit difficult to pronounce. Okay, thank you. First I would like to tell you how we got involved into this competition, because that's what people ask us frequently. So it happens to be that I'm a space geek, so I follow ESA on social media, and somewhere back in November I saw, I think it was on Facebook, that they are organizing a machine learning competition, and it seemed very interesting for what I do for a living. It's machine learning. So I decided to present this competition on our weekly group meeting we have at the institute. So I made this slide, and I said to my colleagues that ESA needs help to this spacecraft worm, because otherwise they will crash it to Mars, because they will not have any use of it anymore. So I presented them my idea how to keep it warm. And as nobody cannot resist a cute satellite with a nice set, I got my team on board. Yeah, and okay, but I had a problem. They didn't know how to make hats, but they did know how to do machine learning. That's what we do at the Department of Knowledge Technologies at Jožef Stefan Institute in Ljubljana. So this is our department. We do all sorts of computer science there, from machine learning, dynamical systems modeling, text and web mining, and so on. We are focused on the development of methods. And we apply our methods on many areas, such as medicine, bioinformatics, ecology, agronomy, business, and so on. And for the first time, we applied our methods in space technology with this competition. So there's a bunch of us, around 25 researchers and 15 students, and now the robot sitting on the desk. We are part of the Jožef Stefan Institute in Ljubljana, which is a leading research organization in Slovenia. This guy in the upper right corner is Jožef Stefan. Maybe you have heard about Stefan Boltzmann law about radiation of black bodies. So this is Stefan, and Boltzmann was his student. The institute was founded in 1949. And if you look into Wikipedia, it says that the idea was research of atomic weapons. But we don't do this anymore, so we do physics, nanotechnology, and so on. And there is about 1,000 of researchers there now. And this is Ljubljana, where we live. So, as you can see, it's quite a beautiful city. It was actually voted as Green Capital of Europe 2016, and I think you can clearly see why. So you can see all the landmarks of Ljubljana on this picture. So Ljubljanica River, the old castle up there, and the mountains in the background. Okay, so this was a short introduction about us, and let's get back to the topic now. So we already heard about the power challenge. So the task was to predict the power consumption of thermal power system for the 4th Martian year, and we needed to predict the per hour power consumption. And for this, ESA gave us all sorts of telemetry data. So we also already heard about that before. So we have this data, and we have measurements of electric current at 33 thermal power lines. The main problem here was that the data as it was given to us was not really usable for machine learning, because all those measurements were taken at different timestamps. So you need to transform this data into a table like on the right-hand side, which machine learning algorithms can use. So you need to align your data somehow and construct features which your machine learning algorithm can use. So you need to decide about the time resolution and aggregate your data in those time windows. So maybe the obvious seems to aggregate your data to 1 hour time steps, because you needed to predict 1 hourly time power consumption. But we had another idea. So we looked at the electric current measurements, and we saw that they are sampled at approximately every 30 seconds. And so we figured out if we aggregate this to 1 hour, maybe we could lose some information. And it seemed that 1 minute is the shortest reasonable time interval, because if you take 1 minute, at least some measurements will fall into your minute. So we decided for 1 minute, and we aggregated the power consumption to 1 minute intervals. Well, obviously, this will give you a lot of data, because we had 4 Martian years. If you do it per minute, it's a lot of data, but we decided to give it a shot and see if we can handle it. If not, then we will increase the time interval. And I think this was the principal difference between us and the other competitors. I think other competitors used 1 hour, at least most of them. So once we decided for the time resolution, we need to transform the data into usable features for machine learning. So you want to construct really informative features. So if we spend a lot of time doing this. So first we focused on solar aspect angles, LT data, and AVT feed data, and we constructed what we call energy influx features. So we wanted to encode somehow the solar energy which is hitting the sides of the satellite at each time point. So in the data we were given solar aspect angles for each side of the satellite and for the solar panels. And if you, for the angles corresponding to the sides of the satellite, if you add P to them, you also get angles for the other 3 sides of the satellite. So in total, you have 6 angles representing each side of the satellite and 1 angle for the solar panels. And then we calculated the energy influx in the following way. So first, we calculated the cosine of any of those angles, and this gives you what we call an effective area of the side of the satellite. So when you calculate the cosine, you get the area of the side as it would appear if you look from the direction of the sun. And we take maximum of cosine and 0 because we get a negative value here. This means that the sun is on the back side of this side you're looking at. And then we multiply this by the solar constant at the time point t. So this is how strong the sun is at the given time point. And finally, we multiply this with the umbra coefficient. So we set this to 0 if the satellite is in eclipse. So if it's in the shade, it doesn't receive any solar radiation. And we set this to 0.5 if the satellite is in penumbra. So this is purely ad hoc solution, a pure guess. And we talked to Luke yesterday, and she said that she uses 0 for penumbra. So probably this could be done better, but it was our guess. And okay, you multiply all of this, you integrate across the time interval you're interested in. So it was 1 minute for us, and you get something what is proportional to the energy influx in this time interval for each side of the satellite and for the solar panels. So we get 7 features here, 1 for each side and 1 for the solar panels. But we also thought that not only the energy influx at given time point influences the thermal subsystem of the satellite, but also the energy influx in some close history. So we also did what we call historical energy influx features. So let's assume we calculated the energy influx for the front side of the satellite. It could look something like this. And then we want to calculate historical energy influx at the red time point here. So if you want to look 8 minutes in the past, we would sum 8 previous energy influxes. And if you want to look 16 minutes in the past, then we would sum previous 16 points. And we considered the histories of length 4, 16, 32, 64, and 128. So this gives you 5 additional historical features for every energy influx feature from the previous slide. Okay, and later we focused on the DMOP data. In DMOP files, we were given information about commands which were executed at the satellite at given time. And from this, we calculated the features which represent the time since last activation of a given command. For example, if you look at the blue command here, it was executed at time point 4. And so for the feature which represent that command has value 0 at time point 4. And then this value starts to increase from that point on. And we increase this value up to 24 hours, so 1,440 minutes. And then it stays like this if the command was not executed in the meantime. So we assume that each command affects the satellite no more than 24 hours. And this gives us a bunch of features because there is a lot of different commands in the data. And now we have also flight dynamics, flight pointing events in the data, FTL features. So here we had information about when a pointing event started, when it ended, and the type of the pointing event. And from this we calculated binary indicators. So those features have a value of 1 when the pointing event is taking place and 0 otherwise. And those are all the features we constructed, and the final dataset looks like this. So we have in total 464 features, like 42 energy influx features, then 400 time since last activation features, and 20 binary indicators for pointing events. And obviously our dataset was huge because we had one minute time interval. So we had 2.7 million in rows in our table. And the file was 7.7 gigabytes big. So this was quite tricky to handle. And we had to use really strong computational power to run the experiments. Okay, and once you have the dataset, you can do machine learning. And for machine learning, we use the random forests method. It's a quite popular method in machine learning because it's very accurate and robust. So probably people who are familiar with machine learning know about this method, and some of you don't know about this. So in the next few slides, I will try in brief to explain to you how this method works. And I would like to mention that we didn't use the standard implementation of random forest. We have our in-house implementation, which is designed for multi-target prediction. So this means that it can predict all of the thermal power lines at once with one single model. The standard random forest can predict only one thermal power line with one model. So you have to build a separate model for each thermal power line. And our implementation is implemented in CLUS software. You can find it on the SourceForge. So a random forest is an ensemble of decision trees. And a decision tree is something which looks like this. So it's a pretty simple model. So you start with one node, which represent all of your samples, so all 2.7 million of samples we have. And then you try to divide those samples into groups which are very similar in power consumption. You traverse, you go across all the features, and then you test all the possible splits across your features. and then you take the best one. So the feature which divides the samples in a best possible way, so that the two groups are very similar in power consumption. So ideally, you would like to have, on one hand, samples which, for example, very large power consumers, and on the other, samples which are very low power consumers, and some feature which tells you what happened at this point and why is that so. And this method is recursive, so you do this you search across all the features, you split, and then you recursively do this for each of the nodes. Again, you go through all the features, split, until you hit some stopping criteria. And stopping criteria is the minimal number of samples you split. So you can say, okay, if I have 100 of samples in my node, I will not split it anymore, this is the end. And then when you have leaf node, so the last node, you take the average of power consumption of all the samples which ended there, and this is your prediction. So when you have a new sample for which you don't know the prediction, you run it down the tree, and when it ends in the leaf node, you calculate its prediction as an average of power consumption of the other samples which ended there when you were building the tree. Okay, and as it's illustrated here, these trees which we're constructing are multi-target, so it means they predict all the power lines at once. So the idea here is to exploit some dependencies between the power lines if they exist with such a model. And okay, and random forest builds a lot of trees. So you have your data, and then you build a lot of trees in a special way. So you you make replicates of your training data by taking by randomly taking your samples with repetition. So you end up with many different replications, random replications of your training set, let's say, like this. And from each of those replications, you construct a decision tree, but you also do randomization on the feature size, on the columns of your table. So at each node, when you are searching for the best split, you take a random subset of your features. And what happens here is that each tree learns very well one part of the space. And then you at the end average or aggregate their predictions, and this usually works way better than each individual tree. Okay, so I hope now you have some picture how random forests work. And other nice thing with this method is that you can calculate feature importance with it. So we did this after the competition, and I included this slide to show the experts what we think are the best features, the most important features for the power consumption. So the most important feature is energy influx on the downside of the satellite when you look 64 minutes in the history. So yesterday we talked with Luke, and she said that this probably makes sense because downside you need to heat a lot because there are the fuel tanks which shouldn't freeze. And then we have some commands in blue. We don't know what those commands mean, but I hope the experts will know. And then we have some pointing events in green, and also this is when the communication device was turned on, I think. So maybe we can later discuss also with you what do you think about our feature importances. Okay, and what I want to show you now is how our leaderboard score progressed through time. Okay, obviously I missed the point which should be somewhere up there. So this is actually our second submission, not first. It was made on the 13th of July, so quite late in the competition. And the first submission was made only with one single decision tree and only with 7 energy influx features. And this was already better than the random forest baseline Alex kindly provided. So this told us that we are doing something good, that our features are probably okay. And Then the next logical step was to move to random forest, and this got us here. And we started with quite conservative settings here. Okay, we used the complete data set here, and we used 100 trees in random forest, and we set the stopping criteria to 1,000 of examples in leaf. So we don't split anymore if we have 1,000 examples in leaf. In principle, we would like to have as much as possible trees and as low as possible minimum number of examples. But since our dataset was very big, we had to go with those conservative settings. And it took us about 3 hours to build the model here. And this was when we used 64 CPUs in parallel. So from here, we moved to here by tuning the parameters of random forest. So we increased the number of trees, decreased the number of minimal examples, but also we increased what was very important, the size of the feature subset which you consider at each node of the tree. So this was quite important parameter which was not obvious at the beginning, because usually you use only logarithm or square root of the features, but we needed to increase this. But everything, all three parameters now increased the running time to 15 hours. So 15 hours with 64 CPUs. And then we made this big leap. So at this point, we were at 6th place of the leaderboard, and we did something which took us to the 1st place of the leaderboard. And what we did, so up until now, we were building our multi-target models. So with one model, we were predicting all the power lines. And then we switched to the standard setting, so predicting each power line with a separate model, and this got us to the 1st place. So the intuition here is that actually most of the power lines operate independently, so there is not much correlation between them. So this is what we think. But this came with quite large cost. So this increased the running time by 33 times. So we had to build one model for each power line, and one model took 15 hours to build. With 64 CPUs, when you multiply this with 33, you end up with, at around 2,000 of CPUs. Luckily, we could afford that because we have some clusters at our institute. So we got one solution in 15 hours. Everything was run in parallel. Otherwise, we would probably still wait for the solutions to compute. And this submission was made one day before the end of the competition. We jumped to the 1st place in the leaderboard, and we were very happy. And then until the evening next day, the end of the competition, the leaderboard was quite quiet. Nobody did anything. And so we were waiting to win. And then 12 minutes before the deadline, Red Rock submitted his solution and jumped to the 1st place. And that was it. This was the end of the deadline of the competition. And my teammates thought that we lost. So they didn't know that the next day they actually have to evaluate our solution on the complete test set. And so they were very sad, and I said, okay, why are you so sad? And then, okay, I explained to them that it's written in the rules of the competition that next day they will evaluate on the complete test set, so we still have a chance. And so next day we spent refreshing the website. And yeah, you know what happened. We jumped on the 1st place. And maybe it was due to our late start in the competition. So we made only 25 submissions, and the other competitors were around 60 submissions. So maybe they overfitted to the small part of the test set which was used on the leaderboard, and we had more general solution. So maybe that happened. Yeah, and Red Rock asked me to share our team experience with you. So this was a really brilliant experience for us. So I cannot remember any project before where we collaborated so well. So we had weekly meetings every week. So we divided the task. Everybody did their part. We joined the results in the end. And we also did night shifts and vacation shifts. So I went to seaside with my girlfriend in that period. So I had to smuggle my laptop with me. And It was also a great learning experience because of the discussions with other teams. They were really open on this discussion panel, shared their ideas, even their code. So we are really thankful to them. We learned a lot. And also we got our 15 minutes of glory. So when the word spread out that we won, we were invited to the national TV station, national radio station. They published a lot of articles in newspapers about us, and we had to do some interviews and so on. So it was also nice exposure of the institute through this competition. And coming back to the satellite, if our technology will enable to give some few more years or months to this satellite, this would be really the best reward for us, worth more than any glory or money. So, for the end, I would like to thank our cluster administrators because they were really supportive. A few days before the end of the competition, we actually support to do this instead of our regular jobs, like writing. Like in my case, that would be writing my PhD thesis. I should finish soon, but this probably delayed it for some time. So luckily we won. Otherwise, I don't know. Okay, and we would like to thank European Commission and Slovenian research agencies which are supporting us through several grants listed here. And before questions, I would like to say hello to Oljaz and Martin if they are looking us through live stream. So hi, sorry you are not here. And if you have any questions, I would be happy to try to answer them. Thank you. And sorry, I would really like to thank ESOC for organizing this brilliant competition. It was really, really great fun and great experience. And I would really like to thank them for taking us to Rosetta yesterday, so we could see the twin of the Rosetta. This was, for me, this was the best birthday and Christmas present combined ever. So thank you.
You're welcome. Thank you. So if anyone has a question and how many computers they used, well, you know the number. How hard that was to organize that in the team or things like that. Yeah, Arthur. Please present yourself where you have the microphone.
Hello, I'm Arthur from the flight control team for Cluster. That's the name of the mission. Mm-hmm. I don't know so much about machine learning, but I would like to learn more about it. So I'm very impressed by your work, and I think you did a very good job. I wonder one thing in particular as compared to the one who made the second place. What we have seen is that you have, the success is attributed to the fact that you use sampling on minutes based, whereas most others use hour based. And I think this correlates very much to the computation power that you have available. And obviously you have a lot of computation power, as you just told us. So I would like to know how to compare, let's say, the one who made the second place, Red Rock. What did he use? Did he also have a computation farm available for his computations? Because I think this is also something that should be somehow taken into account on the resources available for the solutions.
If I may add, well, it could be that we had advantage with 1 minute time resolution, but we really don't know that because we didn't try with 60 hours. Maybe it would also work if our features are so good. We planned to try this, but we didn't have time until the end of the competition. So, okay.
Yeah, sure. So first of all, I think, yeah, I'm the second. I'm Stefanos. So first of all, I think downsampling might have had a big impact here, but looking at the features, I think you had more than just going down to minute resolution. So I think even if you went per hour, it would have been quite good, maybe as good. On my side, I was very fortunate in the sense that A, I used hourly, and B, I had very fast models. So I didn't have neural networks, I had also tree-based models and so on. So it could easily train on my Mac. Sometimes just for speed, I'm not gonna say I used a work computer, but I'm not gonna say I didn't. And that could happen in 20 minutes on 24 cores, but also overnight on my Mac or a few hours on my Mac, that was fine.
And it's really possible to speed up our solution. For example, if you take only the most important features we saw instead of the whole data set, this would considerably speed up the computation. But at the time of the completion, we really didn't bother with that exactly because we had enough computational power not to bother with it. So, but there are ways to speed up this computation if needed.
Okay. I have one more question here.
Yeah, I have a question, Alessandro Donati. Can you elaborate a little bit more on how you organize the team, the roles, who is doing what, and how you were correlated, just from a human perspective?
Okay, so we had a feature construction team, so that was Aljaž, Martin, Bernard, and Matej. And then we had machine learning team, so myself, Dragi, and Nicola. And okay, Bernard was responsible for the power consumption for the target variables. Then Matej calculated those solar aspect angles, integrated them, and so on. Then Aljaž did historical features, and then, yeah, okay, I covered the feature construction. No, and Martin did DMOP and FTL features. And then they joined this, sent it to me. And then me and Dragi were running random forests. Nicola was running XGBoost, but okay, we did submit something with XGBoost, but it didn't really work out because it was a new method for us, which we learned about from the discussion panel, but we didn't figure out how to parameterize it properly. So I hope we will learn this from RedRock today later. But the fun part was that everybody of us had its own favorite programming language. So Bernard was doing in Unix shell, Aljaž and Matej in Python. I was doing C# and Java, and so on. So we had a lot of fun in combining this pipeline. And that the first submission was 18 because some bug in the pipeline. So we had quite a lot of those during the competition.
Yeah. Okay, don't put name on anything. Maybe we have a question first with Ying.
Hello, I come from Kaiserslautern. I'm Otto on the 11th. So I also did a lot of feature selection. For me, it's a little surprise. I did a very similar way like you, but my result, my important feature lists are different than you. For example, for me, the warm up is very important, and also the distance to the Earth. Some startup, but I didn't saw such features in your list. You have somehow totally different feature list. I just want to ask you how you did the feature selection. Did you do the feature selection for each attributes, or because I did that, for each attributes I select a set of features because I think for each target value have different different command. So I was just surprising the warm up are different, isn't not in the list, and also the distance. And I want to ask you how you did the feature selection.
Yeah, okay. The feature importance was done with random forest method, and with the multi-target version of it. So we did feature importance for all the power lines at once. So those should be features which are generally important, but obviously. We had different features than you, I suppose. So I suppose you didn't calculate those energy influx features in the same way as us. So this could be the difference. Yeah, it makes sense to make feature importance for each of the power lines separately. So we would like to do that also. And did I answer all the?
If I may
add the distance, right?
Yes.
The distance is included in all the Thank you. Sorry, I'm Bernard, also from the team. So the distance to the sun is included in all these
features, down panels, front. Because if you saw the equation that Jurica presented, basically all these features include this solar constant, which includes the distance.
And if I may add as well, I'm going to presume that down HIST 64 is the bottom of the spacecraft.
Yep.
Yeah. Okay. So
the
bottom of the space.
Z-axis.
Sorry.
The opposite of where the Z-axis is pointing.
Yeah. That area of the spacecraft is where we do the warm-up operations anyhow. So you're calling it warm-up, and you're calling it down HIST 64, but they're pretty much the same thing.
Okay. Good to know.
Thank you, Luke.
So I'm Sasha Jarowski, and I first might say that I'm very proud of my co-workers and congratulate them. What I wanted to comment was on the issue of computational power, which in the comment turned out like that was the main reason why my collaborators won. This is actually not the case. It helped them win, even they started very, very late, so they could do all of these things, you know, essentially in 2 weeks. But the method that they have been using originally, this multi-target prediction, is actually comparably very efficient to the other methods. And if you look carefully, there was a 0.02 gain at the end. That's in a competition, these things matter, but in practical settings, I think much more can be achieved through direct collaboration, let's say here with the ESA team, who knows the craft, who knows the features that could be generated. So I think there is a lot of room there to achieve good solutions with modest computational power, and we would be able to do them if it was not, you know, 2 weeks during the vacation time. Okay, thank you.
And may I quote Matej? So he said that the computers are muscles and we are the brains. So.
Okay, we had another question. Yeah, go on.
Hi, my name is Gagan. I just want to add a few points what my mentor said. I'm most interested on this target. You said the target is independent of the features. So how was the feature importance, influence on the target like NP, WD 2551 and separate? I wanted to ask about the individual target columns.
Maybe Richard, you could introduce what is the problem with NPWD 2551?
So I think I didn't really understand the question.
Oh, okay.
So, which features impacted on the? Well, we don't know that because we didn't do per target feature importance. So, yeah, we don't know.
Thank you.
Sorry, another question. How many features are you totally used to predict the targets? How many features?
It was on some of the slides. Okay, so we have in total 464 features.
Okay.
Yeah.
Okay, it's a lot of.
Yeah, okay. So in the final results, we used all the features. So we didn't filter out anything.
Hello, I'm Carlos from Telecooperation Labs, still Darmstadt. I just had a question. You mentioned that basically random forest was the algorithm to use, and this was expected as these are the state-of-the-art things. Did you experiment using other ensembles, other algorithms, mixing random forest, SVMs, some other, for example, techniques? Could you elaborate on this?
Yeah, we tried, as I said, with XGBoost, but we didn't come far. We just tried ensembling different random forests with different parameter settings. But this really did not improve, so I suppose you have to have really different methods to gain something from this. But yeah, we just experimented with random forests and XGBoost and combination of the two. Yeah. Okay. This was mostly due to starting very late in the competition.
Yes, yes. There was no chance, for example, to try with SVM models or other type of...
yeah, I mean, we didn't have time. But certainly we were talking about this and whether we should or not, but at the end we didn't because of the time.
Makes sense. Thank you.
Thanks.
Hello, my name is Rui Santos. I work for the ESOC software infrastructure here. Could you elaborate a little bit more on the technology stack you use? Did you use a distributed processing framework or?
Okay, so I don't really know much about the software behind the clusters. So we used, okay, maybe Nicola knows more. Yeah.
Hello, Nicola from the winning team. If you're thinking about something about like Spark or something like, no. So we used actually parallelized versions of the algorithms and just distributed them manually on different cores on a cluster, yeah. Aggregated afterwards.
So you can, each tree in the random forest is independent of each other, so you can run them in parallel. Yeah.
Hi, I'm Ahmed from University of Germany. I had a question about. So I really like the features that you did. One of my questions was for the historical features. Yep. Did you consider to use a model for them, or you just did the simple moving average aggregation for it? But didn't you? Because I faced this actually for the competition. I was using. So I was using moving average as well, but for some of my professors were telling me to use more complicated like modeling for time series analysis and so on, and that would, so I was asking if you considered that in the...
well, actually no. I mean, you could do some decay or something like that, but no, we did just the simplest stuff first and then move from there, but we didn't move a lot
time wasn't
because of the time frame.
Yeah. And I have a comment. So, for example, my colleague here was talking about other models like SVM and so on. Maybe then actually the clusters would have mattered because it would have taken much more time to train them and so on. Yeah.
Thanks. And I think what would be nice to try maybe to combine solutions from different people. So maybe our solution with Red Rock and Alex, I don't know, and do some average of this. Yeah.
Sure.
Hello, my name is Anel de Loza from the Technical University Darmstadt. I have one question. So actually the target values were not known for this last year, but the input values, so the measurements, were known. Yes. So actually you could look into the future somehow. Did you consider this? So did you consider to cheat, let's say?
In what way look into the future? I mean, you cannot look at the electric consumption. Like transductive for semi-super setting or something like that.
You could use this, for example, and the setting of the experiment or the competition is that you can look into the future a little bit.
Yeah, okay, because you're given a test set in advance. Yeah.
Yes.
Okay, we didn't use transductive or semi-supervised approaches, which could use also the test set during the learning phase, mostly because there were a lot of data given. So you use such approaches usually when you don't have a lot of data to learn from, and then you include a bunch of unlabeled data from the test set. But since we had millions of examples, we didn't include also the test set.
And I'll add on to that in that if you're looking at the previous data to try and predict the future, which is what this is about, the cycling of MEX between when it's close to the sun or not, when it's got eclipse season or not, when it's got conjunction or not, you wouldn't have found. So for next year we've got, for the spacecraft, the worst situation is to be at aphelion, when you're furthest from the sun, to have eclipse seasons, so we need to be on battery power, and to have conjunction where we're not doing anything. So the spacecraft is cold because we're not doing anything, and we're pointing it in a manner that it doesn't receive much flux where it needs to. And we've got that, we're facing that next year, and the last time we faced that was 2006 or 17? 2006. So that was 11 years ago. So trying to find, this is one of the challenges within MEX, in that trying to find a pattern or trying to find when something has repeated exactly previously is needle in a haystack. And so trying to find like this, you'd be looking 11 years back, and then it would have been slightly different because the batteries were in a different condition. We had more fuel in the tank, which acts as a capacitor in effect for the heat and so on. So trying to compare two situations and then predict from that is not necessarily the best way, and it's not very easy on mechs. It's a fun mission to work on. This is my boss.
Okay. This is Luke.
Sorry, I would only just add to what Luke had said in that how we operate the spacecraft evolves over the years, and so looking at the past to predict the future in terms of what we do with the spacecraft, how we operate the spacecraft, would be difficult to do for that reason, because we may well actually be operating the spacecraft in subtly different ways. And as we learn more how to use the spacecraft and how the behaviour of the spacecraft evolves over time. So.
Hi, James Eggleston from ESOC. And this is a question to ESA, actually. We've got all these entries, presumably using a wide range of techniques. Do we have any analysis of maybe some of the losing entries that are obviously pretty close, that maybe are very, very accurate in some particular cases?
Yes, that's a good question. We're ongoing analysis right now, and the thing is, I feel like I'm talking like as if I'm asking asked question on ExoMars. But the thing is, everybody has a bad prediction as well, even the winners. So, it's funny what you say, because we try to look at them over the fourth year, and exactly as some periods they are very good, and others they are very bad. And one other thing to take into account is that we have given them a context. So if this context is not representative of a context of the fourth year, then you may have like discrepancies. Nevertheless, they're doing very well, even though we don't cover the full context, because like James said, the operations evolves, so comments may evolve as well. And the thing is that this is a static challenge, so we have given the fourth year and that's it. But the thing is that we can use the algorithm to learn all the time. So every time we have a new context, we have new operations, we can learn about this. And that's one of the great benefits of those kind of methods, is that you can learn on the way. So, but internally we're going to create a document and certainly do a workshop on the analysis of all the candidates and the interesting things, even the bad ranking.
The other thing, when we were designing the competition as such, there was a lot of discussion went on as to how to rank people and on what, and whether to do it on all 33 lines, whether to do it on the lines that I know to be the heaviest users, whether it to be or other factors we put in. We looked a lot as to how to actually rank them, and in the end, this is what we came out with as the simplest for us, but also the most representative.
It's very interesting. I can't resist asking this question. So you mentioned before that the predicting the rate, okay, Melissa Montagnon from ESA, for the mission planning predictions was actually not so close, which we know. Okay, it's computed from a long time ago and quite static and so, but it has margin. And now you have predictions which are maybe much closer, but not for all domains. And as we said before, we don't necessarily operate in the context that was used to make these predictions. So how do you plan to use the result of this challenge for flight?
Yeah, I can introduce something maybe related to what I said just before, is that we can draw a confidence factor on, okay, how much this context was used in the training. So if it was used a lot of time, we can assess that the prediction would be quite confident. We can have quite confidence in that prediction. But then you're applying margins, and I guess you have a word about this.
So from my perspective, or our perspective, when we chose the data set, most of the truly significant changes in how we operate the spacecraft happened prior to the data set. So that, to some extent, remove those as a question. It will be used within Mars Express. We've got the batteries are so old. We intend to continue using the model that I have at the minute, even though the RSME is not so great, and then run theirs alongside. And then it'll be a matter of, as we validate it as time goes on, we'll probably lean more towards one or the other. Could you?
Hi, Alex Leis from Solenix. Just to put the computational power again into perspective, because you said it takes 15 hours, and this is for processing the 3 Martian years already.
Yes.
All of them, and to build up the model. And then for predicting the next year, it takes another maybe hour, or
No,
is this included already?
In total, everything.
In total.
In total, yeah.
So you basically could do that, say every week you could predict for the next year, with a normal machine.
Why not? Yeah.
So I think it's not really much of an issue then with the processing power that you have.
Yeah.
Exactly.
And at the minute, we have sort of a rougher model, and then we refine it. So the rough model goes out until 2020 at the minute, and that will be extended soon. But then for a more refined model, we actually go about 2 months into the future. So using it sort of on a 2-monthly basis or a monthly basis should be okay.
But then basically you can also refine the model as it goes and either prioritize based on experience that you made, specific parameters, and you can get better results as you go. Basically every week if you wish. It's cool.
Almost every day if you wish.
Yeah.
Yeah.
Every night.
I'd also like to make a brief comment, if I may. So we should be aware that the competition as it is not necessarily matching the scenarios for intended use. And some other techniques which we did not use here might be much more appropriate for adopting in an everyday use setting. For example, we have methods for mining data streams. So this means the data are really processed as they come, and the model is updated, is taking into account all of the experience. And for sure, it would not be that accurate. But then again, I'm really not expecting this very, very small margin of accuracy, especially comparing to what the difference is between the currently used model and the best solutions. Okay, we are talking of difference somewhere between 0.5 of RMSE and 0.008 or 0.079. So we can have, they are very, very accurate models which might be simpler, easier to understand, easy to update on a daily basis. And my intuition is that those might be much more useful for practical use rather than those that we actually used in this competition.
Thank you, Sasha. This is a good point because what we discovered is that, like Stefano or Alex, you are using many models and then you are ensembling them. So we can also do that. And we haven't investigated so much some method for cumulative training. So we can add some small part of the data, the new data, so it's faster. And doing some streaming as well. Yep, Alex.
Hi, I'm Alex from Mars Express Flight Control Team. The slide you have actually up there, I was wondering, because this might be of interest for other missions, and this looks like a generic method enough to translate mission-specific data into something that the algorithm or a variation of it can process. Did you actually encounter in any of part of this process a point where you actually had to very specifically hard-code something for the Mars Express mission?
No.
That will be a block for applying this to other missions, or even for other properties,
No,
not a thermal prediction, but something else?
If you have the same context data for another satellite, the process will be completely the same. So the random forest method is general. The feature construction methods we used are also general. So there is no boundaries to apply this to something else.
Yeah. No real boundaries. Actually, we had the same experience on XMM Newton. So we had a PhD student during August, and I showed him how to read the context data, to set up all the things exactly like in the challenge, and he used a random forest on our own facility, and then he showed that to the team. So there's another human experience where when you do that, I mean, when you're saying, okay, I'm going to predict temperatures, this time there were temperatures. So the team was quite reluctant to understand what was going to happen, and they were like not very skeptical that you could predict. But you showed the curves, and that was perfectly matching. So, but then presenting the random forest, everybody understands that it can do the job, and so we did the job on XMM, and we can do that on other missions as well. And we just have to set up the data set at the beginning and how we get the data. Yep. Yep.
Sorry? Will this be available for use in the sense that it would be a generic thing enough that if you actually formulate your inputs, then you can get something out of it?
Yeah, no, not in the short future, but in the midterm, yes. That's the idea. Just click a button and you get your prediction on targeted values. And the idea is that we can have the context that we've seen for Mars Express can be the same for other satellites. Yeah, you have some parts that are the same, how the sun behaves or things like that. And but then you have to adapt the solar aspect angles for each spacecraft, but the source of the data is the same for all the spacecraft somehow. So we have to work on this as well. That's I guess that's our main challenge, because now we have solutions. We need to trigger with the data access. Any other questions? Yep. One and two.
Yeah, Elder from Frankfurt Analytics from Meetup, and I have a business question because why we are doing all that, because at the end of the day it's interesting for me to know what was the value of what the guys actually did. Yeah, so to say return of investment, because it's time, it's it's money, so it's just interesting. What was the ROI of the whole competition?
So do you mean for us here or for the guys? We get to extend the mission. I get to be able to say we have enough power available that we can continue doing science. I get to say that when the next eclipse season comes, which 2017 is horrific, but 2020 is also unpleasant, I can get to say, the question will be asked, do we have enough power to survive the eclipse season? Do we have enough power to survive the eclipse season, and how much science can we do at the same time? Do we have enough power to survive the eclipse season and be able to do science thereafter? And I get to say yes or no. So we continue to do science or not. I mean, it's a fundamental survival issue for MEX. So that's what we gain. And my boss will say something.
I just want to say that we do planning at at many levels and many timescales, and part of what we do at a more strategic level is every so many years we have to apply for more funding, and we have to be able to say to the powers that be, Mars Express will be able to continue operating until the year 2000 and whenever, and this feeds into those predictions and that process. I mean, then in addition, at a more mundane, more operational level, we, as Luke has already referred to, we know that in the next few years there will be very challenging conditions for Mars Express. We have long eclipse seasons with long eclipses and declining battery capacities, and so we have to prepare in advance how we are going to operate the spacecraft in those challenging seasons, and this is something that we are doing right now, and this model will help us to perform those predictions, and will help us to decide how to operate the spacecraft. And I should say that in doing so, that will not only optimize the amount of science we can produce, but it will also help to prolong the lifespan of the spacecraft.
Thank you, James.
Okay, we have one last question.
Yeah, I'm David from TU Darmstadt, and I have a question about the mission time, because all equipment obviously have a life cycle. And as Luke mentioned, batteries are degrading and solar panels are degrading, and basically all the electronic devices, installations, whatever, are changing during a mission time. And I remember that when I just visualized the data, plotted the diagrams, and then checked the correlation, that some of, probably even the main contributors, I'm not so sure about it, but some of them, apart from their ups and downs and different cycles, they had kind of a trend going up or going down. So have you thought about, or have you actually looked into using the actual mission time as a variable, or would it make sense?
Do you mean the age of the mission?
Yeah, the age of the mission, yeah. The age of the mission, because these effects, so these effects like the degrading battery, yeah, these change with the age of the mission, and so I'm just wondering whether that would be a reasonable addition or something to look into it on top of all the other features.
So potentially, you have to appreciate, I see things as an engineer, and it's what I can see.
Yeah, that's why I'm asking.
And you see things as the data analytics. So
I think it could be useful. We were also thinking about this to encode, I don't know, time since beginning of the mission in weeks or months or something. But at the end, we didn't include this into the data. It got lost somewhere during the process. Yeah.
Part of the reason why we gave 3 years, 3 Martian years, is that, I mean, that's 6 years to 8 years. In this way, you get some of that degradation. It's included in the data anyhow. Yes, you're right, some of the equipment no longer functions as it did. This is why we have the beginning of life with the batteries, for instance, and the end of life. The MLI also begins to decay over time. The glue that's holding some of the heaters on also begins to crack and decay, and that comes off. There are many factors we could add more in. I would not know how to quantify it, like the degradation of the MLI or the glue and things like this. I really wouldn't. It would be something that could be tried. We gave a lot of data as it was, and we thought perhaps that was at least a good starting point.
You will see in my solution, I used the time since the start of the mission as a feature, and it worked. It was useful for the neural nets. They picked up some trends, and I will show some details on that later.
Well, thank you all. Yeah, it's time for something before lunch. We have the head of strategy here today is Mike McKay. He knows everything about ESOC and is going to take half of you to a tour. Of course, not the ESOC people, because you know the site.
Well, they might learn a few things too, but anyway.
You're welcome to join. So please, all the candidates and invitees, can you stand up just to see how many of you are? So how many can you take? Split in two. So can I have 10 people out? So we just split. Yeah. 10. Just count. I have to count because it's not self-counting. 1, 2, 3, 4.
Tell me, who do we go with?
5.
We go with this guy?
Just stay here. Yeah, just stay here. 6, 8. Yeah. 7. Stay just here. 8, 9, 10.
We've got 3 tour guides. So they can
oh, perfect. Okay, you can go with the first one. It's just you're good. Okay, Mike, I'll let you take those. If you can move.
How many?
10 by 2.
3 10? You've got 31. If you'll take 10, and then Simon can take 10.
Martin, so.
So you're making 2 groups or
3?
3.
How many people are thinking?
33. 35.
How many people wanted to?
All of them.
Right, then yes.
Don't you want?
Yes, take a group of 10. 10
splitting in groups, right?
Yeah. If you can you auto-organize yourself and have 2 groups here?
Split. Which size?
About 10.
Okay.
They're coordinating between themselves as to who starts where.
Okay.
Start Rosetta. Okay, you start Rosetta. And then.
just take one with us.
So this is a video for the 10 years of Mars Express. A quick overview of the history of Mars Express from 2003 to 2013.
one winner. We were waiting for you.
Three, one, two.
Okay, everybody. We have one word from Eldar, who's the organizer of different meetups, and is caring about the FFM Analytics meetup group. So I'll let you.
Do you have any like PowerPoint? Any? I will just type the address. Any slide? Yeah, we'll just type the address.
Firefox, you mean?
Yeah, if you have internet.
So everybody's sitting on history.
There's no porn there. Analytics. ffm.org.
Oh, okay.
That's it. It's in French, yeah? Okay. Yeah, guys. Me, myself, and two other guys, we are running the community in Frankfurt, but it's not limited to Frankfurt. It's the whole Rhine-Main, and we are organizing monthly events, and we are quite techie guys, so topics like machine learning and any data science related are always interesting for us, and we are already doing it for the almost 3 years, and we did already 14 events. And for the first time, we were like 4 people sitting on one table. And for the pre-last event, we had about 90 people visited our event. So the interest to analytics and data science in whole Rhine-Main is really rising. And we have very talented guys. And a few of our guys, they're probably here already, I can see. And the winners, for example, who are in the top 5, like Alex and Stefanos, they're also from members of our community, the contributors. And yeah, we were really successful. Right now we have, you can see here the 780 members. And what's surprising is that they have really, really good experience and background in analytics. And we love ESA and we love data science, and it was really a pleasure for us to bring awareness about the ESA and about this competition to the Rhine-Main event, and that helps, that worked pretty well. And yeah, thank you for that. We're looking for more competitions like this one, and if everyone is living here in this area, you're welcome. You can just go to analytics-fm.org, and it will be redirected to meetup.com. You can also search us on this website and just join us. We will organize the event in November. The topic will be artificial intelligence. Yeah, so please welcome. Thanks.
Thank you, Eldar. Oops. That's it. So we finished the break time. Some of us. And we look at a video to show you. We were talking about the sorry, take a microphone. About the VMC, which is a webcam on board Mars Express.
You have two mics and I can hear you through neither.
No, me neither.
Come back here and have a chat while I where's my video, by the by? So you talk.
Yeah. So you want the videos here?
Okay, thank you. This one?
Go. No, second one.
That one works. Try that one.
Whoa. So she's going to show you a video of the onboard webcam. So you can imagine the technology. I mean, you will talk about that of this webcam. Get this away.
Sorry.
Okay, then go for it. I mean.
Okay, wait. Let me start this again. So the history behind it is that Mars Express has a small webcam on it, and you have to take into account that Mars Express launched in 2003, and this was old technology in 2003. So it is. Don't consider any webcam you have now. This is the eons old. This is when we use cameras with film and stuff. And the purpose was actually for checking when Beagle deployed to make sure that Beagle did deploy and just to see the progress of that, which it did. And then it was left as just sitting on the spacecraft, a little piece of kit. It's been reinstated as such. It's now actually considered a proper scientific instrument. But for a while, we got to play with it on Mars Express. It was our sort of instrument as such. And I wanted to show you one of the videos that we took. So you can either take an image with it, or you can do sort of every 5 seconds. And this is an orbit. And the Mars Express has a highly elliptical orbit, so this is what you will see. And we like it. It's just simple as that. We think it's cool. Also because we get to play with it. So highly elliptical orbit, and it starts there. So you can see the pole already. And we come in towards the planet, nice and slowly. And then straight into very close to the planet on the dark side, and then we come back out. And look at all the features that you can see. It's just stunning. This is the planet that we get to explore day by day. I think it's amazing. And with your work, hopefully we'll get to do this for somewhat longer. Yeah. So that was all. I just wanted you to see that. I think it's quite cool. Right, back to you.
I invite you to check the size of the Grand Canyon of Mars. You have some pictures with the overlay of the canyon over the USA, and it takes the whole range.
That, for information, we're going to have a quiz. That might have been one of my questions. And
I didn't hear that.
No, you didn't hear anything.
Anyway, to continue.
Okay, so we have a space and data quiz. Please, Jose, can you come in? Yeah. So anyway, those are the pictures of yesterday, while Armel Hugo invited us to visit Rosetta. So here on site, now you've seen through the visit that you've seen Rosetta behind glasses. The winning teams saw them, so that's for real, and they could touch it with gloves. And so the nice thing is that Rosetta resembled Mars Express very much, and we could see the back of Rosetta, which you cannot see from the windows, where the Philae lander was sitting. So that's quite nice. So I was there also. I was like a little boy somehow. So we have some space quiz questions and data science questions. Easy ones.
Less questions.
Yeah. Okay. I won't say anything anymore. And you can start.
Do you want your questions first? We'll do one each.
I don't know. She starts. Yeah.
I start?
Yeah.
All right, so, there it is. The way we're going to do this is hands up. Whoever gets the answer right, you get a goodie. But there's one preparation. Can you put up the page with the number, the 1,180? So, this question sits there and stays. You get a moment to consider that whilst I carry on with other questions. The question that is related to this is, that is the present distance between Mars Express and us, give or take a very small amount. We command Mars Express via very large dishes, generally. And I'd like to know, if you know the distance, you should be able to tell me how long it takes a command to reach Mars Express. And I want a number, I want a period of time.
Yeah, 22 minutes.
To get there?
20 minutes there.
Okay, any other?
7.5 there.
Yeah, keep going. 24. Okay, so we can keep on guessing, but I have given you the number for a very specific reason. If you consider there must be some physicists in the room, at least you must have some physics background, you will know the speed of light and radio propagation, you know the distance, therefore you can tell me how long this will take. I will let that question sit there for a minute because I don't expect you to know it off the top of your heads. If you can do that off the top of your head, brilliant. But meanwhile, I'll go for another one in between. I'll come back to that one, okay? So we start with a nice question. On which body in the solar system do we find the largest quantity of water? We work in interplanetary. This is the sort of stuff that we have to know. Yes? Europa. Yeah, close.
Europa there?
No, no, not at all. Not at all. Really? No, not at all. You've come to the European Space Agency. Come on, guys, you did some homework. What? No, no.
No.
So, again? No, but who said you were, one last guess? We read had a Europa. Titan has water, but no. So, who said Europa first? Why?
Because Europa has a massive ice sheet, and we still think that we know now that underneath there's basically water.
Yeah. So Europa has a lot more water than Earth, at least 2 or 4 times. But the other moons of interest? No, Io is a really interesting moon. That's hugely active, but it's not Io. Right, next time we invite you all to the European Space Agency, and you're coming to do interplanetary, okay, I'll send out a homework sheet beforehand. No, that's one of the other moons, but it would have been Ganymede. No presents for anybody. Your turn.
She's just an engineer, no answer. No, okay.
Luckily, my questions are easy.
Yeah. So, yeah, well, I can start with the first one if you want. Yeah. Yeah, I did some stuff, I think. So what you spend your time first when you're doing data science, when you're facing a problem in data science? I have some suggestions, but yeah, tell me. Google. Yeah. Domain understanding, that's what you say? Yeah? Processing? Well, that's my favorite. I mean, getting domain knowledge. And of course, before that, you should get good coffee. So, anyway, I'm quite easy with this.
Wait, whoever said Google it, I think they should get.
Another one for Google.
I'm not a flight dynamic guy. Okay, next.
All right, a nice one. Name the first man and woman to orbit the Earth. You have to know this. And? Okay. Whew. Yes.
Who's getting it? Your boss or you?
Okay. Data question?
Data question? Go ahead, we'll say it.
Super easy one. What's overfitting?
This is not fair. You should not allow data scientists to answer.
Exactly. Maybe if non-data scientist is here in the room,
yeah,
you're giving priority.
Yeah, giving priority. The others giving nothing.
A balloon is.
So yeah.
Another data scientist
Yeah.
It sounds like if you train a model like too much and it like over guesses, like it tries to find stuff where there is none.
Yeah, somehow.
Sort
yeah,
of.
Somehow. Or when you train too much on too few data, and it's only learning the noise of your thing, so you're overfitting.
I think it was good enough. Huh?
Yeah, it's a good answer.
I'm getting better.
Can see that.
Right, I'm modifying my questions as I go. That one we've already got. That one you've already told them.
Okay.
Tallest volcano in the solar system, where is it, and what's its name? Say again? And the name? Do you know how tall it is as well, for extra bonus points? 20 miles, elephants, what?
24 kilometers.
So, the 24 kilometers, it's 25. So you get the bonus point. For which there's a magnet. But you get the... You're welcome. Data question?
Yeah, I think everybody understands this is an interview, okay? Go ahead, Jose.
No, it's
yeah. So easy one.
Back.
Up there.
Yeah.
Decision trees.
Sorry?
You said ensemble of decision trees.
Ensemble of decision trees. Any other?
VMs.
Good.
Yeah, sure. Yeah. Yeah. So we put different solutions, but
yeah, I think examples of trees is also a good answer.
But if you say no, this is a cooperative interview.
So, don't snigger, I haven't started yet. This one is not about space. It's about the European Space Agency. I don't know how much you know about it, but the European Space Agency is funded by various European nations. That's how we get to be here and how we get to do the work we do. Depending on where you're from, you are probably paying for us to do the work that we do. How many nations are part of the European Space Agency?
Count the flags.
Dear everybody, please meet my colleague over there.
22. Alessandro, the answer is?
Yes, Alessandro. 22. We agree, 22?
Should we consider sigma or something, or?
So 22 or 22?
Wait a minute, who?
2205. Let's count.
Yeah, 22.
So,
22.
I would say that in general, for the past few months on this challenge, it has been quite pleasant to work with Red in general. It has been good and cooperative and productive and constructive and all. However, in this particular moment, I see another side to him completely.
Okay.
So we are 22 nations that are fully paid up, but we also have some cooperating nations, in particular Canada. Canada has a great space agency and can do remarkable things. So we have a cooperation with them, but they're not fully funded, paid up members in the way that Germany or Slovenia and so on are. Would you care to? Well, you can all count, and he gave the answer, so I'm not giving out anything for that one either. I'm sorry, you can go somewhere.
Maybe it is only deserve pins. Yeah.
We should not disturb anything. Who said 20?
Everybody who could count, apart from you. He already got a prize.
It's an interview.
But not for the All right.
So, data question now.
Jose?
This is your favorite one.
Yeah, this
Come
is a
on.
very... The trolling question. Oh, there, okay. Ying. Okay.
Okay.
Yeah. We got a reluctant innovator.
I think for a sense of humor at least, we ought
yes,
to...
you win as a penis.
Yeah, I think this is the best one.
We had a correct answer as well. So the humorous one and...
Exactly. Any other language? Of course.
Hold on, what about Python?
They said already.
They did?
Yeah.
So yeah.
Okay.
Sure. Assembler.
Yeah, you see it.
Yeah, everything is there. We have said anything.
What's the fun answer?
No, I have 2 more questions. So I have one question which I'm going to explain the answer to because you didn't do your homework already, so I figure we should just do it this way. The question is how much... Oh, there's my boss here. James? No? Okay. How much of the surface of the moon can be seen from the Earth? Yes?
More than half.
Well, that's good. That's between 50 and 100, so... But it's an excellent first start. It's either more than 50 or less than 50%. Any advances? Okay, why more than 50? More than 50, less than 75. Why more than 50? Indeed. Exactly. So there are 2 reasons why it's more than 50. One is depending on where you are on the Earth, you have the parallax effect. And the other is that because the moon, the orbit is not entirely round, it is slightly elliptical, then you get a slight precession. So you can also see a bit more that way. So that turns out to be actually 59%. So yes.
Oh, sorry. Oh yeah, my computer.
Presents.
Okay.
Prizes.
Oh yeah, sure.
And the last question, other than a magnet, nice that you share. If we come back to the 183 million and la-di-da-di-da.
Yeah.
Yes, just one way. So I'm impressed because so I'm in a room of data miners, yeah, and mathematicians and the like, and I stand as the engineer. So I think, okay, there's the distance. I know the speed of light. I simply do a division and I get my answer. I see that you guys will go, there'll be I can either guess it or there's a machine where I put in one number, boom, model, and out comes the, as a different way of thinking, I quite like this. But it is, so yes, you have your distance, divide it by the speed of light, and it comes out with, well, this 10 minutes and 12 seconds, 13 seconds at the minute.
Okay, 10
and
minutes.
I think that's it.
Over there. Oh, over there.
Was that a guess?
You said 10 minutes?
Someone with it.
I counted with my fingers.
Some understanding.
No.
Okay, and then I think
we're done.
Thank you for your participation. If you do come back, like I say, do homework before. You're welcome. Yes. Oh, for the interview? Well, the interview's gone, so sorry, but just now. Yeah, no, you don't. I'm really sorry.
Okay, so now we'll give the voice to Stefanos and then Alexander Bauer. So first, Stefanos, if you may, I will put your presentation on. So Stefanos is the runner-up. Well, he was the first one day before the end. So I think you can manage this full screen mode. And I think you have this. All right. Don't make it seem I'm small.
All right, so I'm Stefanos. So I work in Frankfurt. I'm originally from Cyprus, but for the last 4.5 years, I've been working in Frankfurt in the financial industry. So I work for an algorithmic trading firm. So I was very happy that I actually got to do something meaningful for once. And I'd really like to say thank you to ESA for this competition, because I think it was fun. It was like good for both sides. So you got something, and I think for the competitors it was very enjoyable. And my congratulations to the winning team. It's nice to have new arch enemies. So thank you. So I'll go briefly then into a recap of the competition. So I spent an unreasonable amount of time on this slide. So there is a library that can kind of plot like XKCD, the webcomic. So I don't know why I did this, but you can kind of see how it progressed. So I started with a benchmark, but benchmark really just predicting the mean of each power line. So really like the stupidest thing you can do. I mean, a good start, but there's no input from the context data at all. And then I'm very kind of impatient, so I did almost all the work at once. So I did a lot of feature engineering, and immediately went into extreme gradient boosting, so this XGBoost library. And that's why we have this big jump now. And already now we are at the 0.1. Now the next discovery was this big power line, the 2551. Once we find the link between that and one of the subsystems, ATTT, and that gave a big boost. And we have a long, I say laziness there, but it could be that I'm trying to get something, but I'm not getting anything better because it shows the best score. And towards the end of the competition, this guy's joined in, Alex was really advancing, and I believe Fornex was really doing very well. So then I said, okay, it's time to work on it. So I added some more feature engineering, and here I played a little with lagging the features, and finally one of the last jumps is when I used an ensemble where I basically had extreme gradient boosting, and I added to it another method called extremely randomized trees, just took the mean, and that helped a lot. Now it's funny, like that final night of the competition, I wasn't, so I was already on vacation and I wasn't home, and I think it was 10:30 p.m. and I was at a restaurant and my boss showed up and he was sitting at the table. So thankfully in Frankfurt restaurants close at 11. So I had a little bit of time, I went home, and really a few minutes before the end I was able to do that final submission. So I'll show it in a diagram, but it's essentially this ensemble with XGBoost and some data bagging. So here is some tools I use. So it's the classic Python, Pandas, sklearn, XGBoost, and I really like these Jupyter notebooks for interactive work. And I'll go quickly through the features. You guys did a really good job at showing what you did, and I did a lot of the same stuff, a lot different. So sometimes I didn't know what I was doing. So for instance, that's an example where this LT data, I added an indicator function for conjunction. But then I even tried this Sun-Mars Earth angle, making it also go negative. I didn't know if it would help, but you can see there's a lot of trial and error. And then I removed some proxies, so some features are essentially one explains the other. So distance of Sun to Mars and the solar constant maybe are interchangeable, and so on. Now you had the winning team showed extremely nice features with solar aspect angles, and here was a point where I did nothing, because I thought when you use decision trees, they are extremely good at picking up interaction between features. So I gave the model a lot of responsibility, and I thought, okay, you can figure it out. And I don't know if it did, and sometimes it's better to make the feature explicit, so probably there would be some value in doing the cosine transformation. Here we go to the events files, and here you did the opposite, the winning team did the opposite, so I made the feature more explicit, I think, here, because I counted how long we are in Umbra, so I kind of had a stopwatch, and so time since Umbra, time since penumbra, so under the hypothesis that the longer we are in it, the colder we are, and so on. And maybe another example of a feature is the very top one. That one I called time to pericenter. So that one shows essentially where we are in the orbit. And what Lucas said, that maybe the albedo would make a difference here. So that feature should pick it up. And this is the flight dynamics features. Here I made a mistake. So the proper thing to do was to have an indicator function because we had the start and end. And all I did here is I just multiplied the feature by how long it was there. And I thought, I'll do it later. You know, we have plenty of time. Completely forgot about it. So this isn't the final solution. And here was maybe a point where domain knowledge was important, and a point where it was very hard for competitors because we had this subsystem commands, and we know that the 4 characters represent a subsystem, but the rest is a signature. So what is tricky here is that some of these are on commands and some are off. So if you just treat it as a subsystem, then you can see like on and then on again, which might be confusing for the model. So maybe the part where I did a little bit of manual work was trying to find the on and off pairs. Yeah, so there is some brute force here where you can see this on the bottom slide, so it's some code from pandas here. I'm essentially sorting by subsystem, and I'm counting how many events I have for each single command. So, and sometimes it's obvious that a couple are pairs just because the number is so close. It's usually not perfect. And maybe one step further, so once I had this, then I could make a binary function with the pair. Maybe a step further would be to have it automatically turn itself off if you're missing the off. Maybe if it's being on for a little bit, just turn it off automatically.
But just to confirm, yes, I mean, the nature of what we did is that we gave you all of the thermal data, all of the power data, but we didn't necessarily want to give you all of the commands and the exact commands because there are hundreds, if not thousands, and it would not be useful to what you were actually doing. The first 4 letters will be your subsystem, and then the last 3 numbers are the 3, 4, are more explicit. But yes, you will often find that if we have 0, 1 as on, either 0, 0 or 0, 2 might be off. That's how we started. However, as the commanding has evolved, sometimes things have changed slightly. Yeah. But yes, in essence, this is the way to go.
Yeah, it was quite interesting, though, to go through them. And maybe here we can see the effect of if you actually find one of these binary pairs, and you can turn it into an indicator, then things become a lot more clear. And now this is the line NPWD 2551 against subsystem ATTT. So if I just use now the first 4 characters, I would get the scatter plot on the left.
Yep.
So with side imagination, you can guess there is negative correlation there. But then if I found this pair there that I'm showing, which is 310A and 310B, then the kind of correlation becomes more clear. Yeah. So I think this helped, but not as much as I thought. I thought it would be like a deal breaker, but it definitely helped. And another thing I did is trying to kind of include some memory into the system because something can happen and then the power lines can react much later. So I think Alex had the very beautiful, and Keith had the LSTM model, which is very elegant and has memory on its own, but in my case, I just included exponential weighted moving averages. So for every single feature, I had its version in exponential weighted moving average, And also, I wanted to have the difference. So kind of to tell the slope.
Mm-hmm.
So let's say if you know your height, you could be the very low height, but you are trending up.
Yeah.
So that's what that plot over there shows. And the difference is taken from the current observation to the exponential weighted moving average. So kind of one parameter, the decay of the exponential weighted moving average determines both of the new features. So if I had, let's say, 80 features, at the end I had 80 times 3 because I have them in 3 incarnations. And yeah, this is an example of all the features. So you see a bunch of them, I just labeled them as pairs. And then you can imagine now a second copy of them for EWMA, a third copy for differences. Now for models, like I mentioned, I use gradient boosting trees and extremely randomized trees. What was very interesting is random forests with gradient boosting was not as juicy as gradient boosting with extra trees, which I found very interesting. I'll talk about it a little later. So I'm not going to explain random forests. You guys did a good job. And here I just wanted to explain the difference between random forests and extra trees. So a random forest, when it splits along a branch, it will optimize the split. So here we have an example where we are classifying between cat and dog. So it says if the height is bigger than 50 centimeters, probably a dog. But in an extra trees algorithm, this split will happen randomly. And my I don't know for sure, but I speculated that my extra trees gives a better ensemble because the random split gives more kind of diversification, less correlated trees. But I'm not sure about this, just a hypothesis. And I'll try to give, because we have a mixed crowd, a bit of a tour of gradient boosting, but with a lot of shortcuts, so please be nice. So in a nutshell, gradient boosting is essentially adding trees, making sure every tree you add compensates for the shortcomings of your previous models. So I think this is very natural. It's like if I'm studying for an exam, I'm going to study the things I don't know. So you concentrate on your weaknesses. And this kind of in literature started, it's not a new thing, it started already late 80s with this question, can we combine a bunch of weak models and get a strong model? And then this guy took a couple of years, but he had an answer. And then a few years later, the algorithm called DataBoost came to life, and I'll try to describe it here with this, here combining 3 classification models, all of which are very weak, gives you a very strong one in the bottom. So we can see on the top left, we want to classify positive and negative observations. And we do 1 split, and we get a couple of the plus signs correct, 3 wrong. So for the second iteration, we want to cover for these weaknesses. So what we do is we give a lot of weight to the 3 plus signs we got wrong to make sure the additional model will actually get them right. And you see, once we make the second split, it got those right, but then it got those circled negatives wrong. So again, for the third one, we give a lot of emphasis on them. So essentially, this is a process. So always adding a model that compensates for the previous models. And that example was for classification, but for a regression task like what we had, one way to kind of get an intuition is this. So we can have a model. And in this case, that's a prediction right there. And the true value is shown as, let's say the first row is 102.5, prediction is 101. So our error is 1.5. So how can we improve this now? So one way is to train a model whose job is to predict not the true value, but the error that our first model got. So we train a model to take in this input of x and predict 1.5, 5, 1.2, 0.1. And this model will come here in blue. So it's a new tree, let's call it age of x. And this is an optimistic, I just pulled these numbers out of thin air, but let's say you can do this. So suddenly we have an ensemble. We have a boosting here, gradient boosting, and we managed to reduce the error a lot. and we get a new residual which is much lower. And this is essentially the whole idea behind gradient boosting. And the name gradient boosting comes behind because of kind of a convenient fact that when we close the residual, mathematically this is the same way as moving downhill in a gradient descent algorithm. So going towards the minimum loss. So for this, I used XGBoost, and most people in competitions these days use XGBoost. They love it. And it's basically an extremely optimized implementation of boosted trees. It's very fast, very scalable, and lately, especially on Kaggle, it's really in every competition, all the top solutions use it. So I think if you have to go on a desert island and you can take only one algorithm, this one is a good one to take with you. And I think it started maybe with the Higgs boson competition on Kaggle when this was developed, and then it picked up. So I'll go straight into how the final product looked. So I'm showing here the features I used, and then they get merged into kind of my full big data frame that I'm going to use at the end. What's interesting is I trained on hourly data, but all the feature engineering I did in full resolution. So the resampling to hour happens at the very last stage. And it was pretty easy to do this even on a very weak machine. So just create all the features with full resolution. At the very end, add the delays, the lags, the differences like I've shown before, and then go for the training. When I was training, and this is now we're at the purple box there where all the data is merged, and now it's hourly. For training, I did this funny thing here towards the end of the competition where I noticed I had a lot of variance depending on which data set I used. And one way to, the classical way to reduce variance is to do some bagging, of course. So, excuse me? Yeah, they're good variance reduction, so this is kind of one more layer or one more dimension. And also it's a little manual in the sense that it allows, so usually in these things, and I come from a finance background, so usually the future is very close to the recent past. And here is, I think the operations in this future is very close to the recent past, which is the third year. So I wanted to oversample it a little bit. And this is what this does. So I have here two moving averages, but I also have doing all the years, so the full training data, first year, second year, third year, and then only the third year. Because in the third year, kind of mission operations changed a little bit, and I wanted, it would give a lot of variance to the training, so one way to reduce variance was to train it on its own, and then do some bagging with the existing full training set. And at the end, every data set merges into this pair, just doing XGBoost and extra trees, taking an average. And at the end, you see I have 8 models and a simple average of the 8. I tried to do some stacking, so having a machine learning model trying to predict which of those I should use at any given time, but I didn't get much benefit. So then I went for the simple average. Here is just for completeness here. I'm showing some of the features for the best submission. So I was doing some manual feature selection. And these are the ones I ended up with. And I think a lot of them quite similar to the winning team. And what was also interesting was this is done one feature set for all the lines. And then after the competition, I was kind of reflecting on what happened, and I thought, okay, can this be simpler? And I checked some other ways, and one other way is instead of doing this manual feature selection and these multiple data sets, what if I had an automatic feature selection per power line, and then I fed that to a single training set and went from that point onwards. And that one, I mean, this looks even more complicated than that one, but it's actually simpler, I promise. All I did here was I used extra trees, a round of training with extra trees to pick the best features. I would choose the top 40 features, and then no data bagging, and this would give a very good score, 0.082. So this is kind of a simple model, and almost it would have landed in the 4th place in the public leaderboard. And then even simpler, if I did a single XGBoost, that would have been 0.090 in 7th place. So this is kind of along the lines of the Q&A before. So sometimes for production, a very simple thing can do the trick, but for a competition, it's a much different game. But interestingly enough, the auto feature selection was giving things like, for NPWD 2551, it would choose the subsystem, ATTT. But for the line that was trending upwards across the years, it chose Unix time as its best feature. So essentially, it regressed across time. So it is a reasonable way to go forward if you cross-validate it and do it properly. And that's it. The code is available on GitHub. And if there is any questions, of course, you can email me.
Thank you, Stefanos. We have 5 minutes for questions. If you have some questions to ask to Stefanos, we already talked a lot, so there, okay.
So, hello again. Yeah. So we saw that in the end you flipped from the 1st position to the 2nd position.
Yeah.
Why do you think this happened? Was it because of maybe overfitting to the public test set, or why?
May very well be, but what's interesting is that almost everyone kept the same score, like to 2-3 decimal places. So this I don't have an answer for. Like, I think positions 2 to 7, if you look at the scores, they are very similar. And then usually with overfitting, you in the test set, in the hidden set, you get a worse score. What was interesting, the score stayed the same, but magically the winning team had an improved score, so they did even better in the out of sample. So I don't have a sure answer, but I did have a lot of submissions, and part of the motivation there was that the competition rules stated that the best submission would be chosen. So from kind of a game theory perspective, the best thing you can do is just throw many in there. Yeah, but I think at the end it was not terribly overfitted because it was very correlated to my cross-validation set, and the public leaderboard and the private leaderboard showed similar scores. So every time I would see an improvement, it was really a real improvement, and I could see it in all the measures I had.
Okay, thanks.
Yeah.
So you seem to have quite
Wait.
You seem to have quite some domain knowledge. You seem to know what the subsystems are and all of these things.
Actually, very little. This was all brute force, kind of.
Huh. But yeah, I had the feeling that you understood these things.
No.
Okay.
No.
Okay, then you fooled me. Thank you.
That's the magic of the data scientist.
But the correlations that you pick out are true. This is, for me, one of the really interesting things. I know this stuff because it's my spacecraft and I see it and I monitor it, and this is what I have learned. But I give you a bunch of data and you come out with the stuff that's true. It's interesting for me. It's a completely different aspect, but you look at it from a completely different perspective to me. But you come out with some of the things are just absolutely true. And other things I'm looking to see what else you found, because there'll be things that I, with a human brain, have not been able to pull out, but through crunching through numbers, you have.
Okay, thank you. Thank you, Stefanos.
Okay, thank you.
We can close. And now we have Alexander Bauer, codename Alex. Very original, Alex. He's going to present us his solution. Oh, maybe we should have.
Control L? Okay, all right. So hello everyone. Thanks a lot for inviting me to show the fourth place solution.
You're welcome.
I'm in the luxurious situation that I don't have to explain everything because a lot of the things are actually quite similar. But what I want to show, instead of going through the same features again, showing the aspects of how to get to those features, so kind of the mental process of feature engineering, and I will show a bit on how recurrent neural networks can be applied on this. And from my background, I have an electrical engineering background, and I did a PhD in satellite image interpretation, so I should have some domain knowledge, but I never worked with thermal systems, and as the commands were all kinds of anonymized, didn't help much to incorporate that. So there was also a lot of data mining involved. So yeah, I think this one we pretty much covered. But when I started the competition, I thought, okay, maybe this is an isolated system, it's in space, and it should all be deterministic and predictable, yeah. But actually it's not, and because there's not only dependency on the environment, but it's also on the operation that is happening, and of course systems degrade, they change over time. And there's quite of unobserved information also in there. So I came up with a bit of a mental model how a thermal system actually works. And when you look at your iron that you have at home, it's pretty much also a thermal control system. So you have a reference temperature that you set up on your wheel, and the system compares the measured temperature with the reference temperature. Then there's a controller. Can be something very fancy, but also something that just switches on or off. And then you have the physical system that's then what you iron, how much water you have there, and that influences how the temperature then changes based on that. And we have some environment information, we have all the operation modes kind of in the DMOP signals and stuff like that, but we never know the real temperature that is currently in the system. And that's why you have kind of a lot of unobserved information and a lot of noise in there, I thought. And also you need memory because temperature kind of distributes slowly inside a satellite. So these was kind of the challenges that I came up with before I even looked at the data. Yeah, and so I did my first iteration. I thought, yeah, let's do some basic feature engineering just on each data set. Take the very obvious things. And I also looked at the top 5 covariance, top 5 variance signals and see, can I find some characteristic that could be useful for the feature engineering? And what struck me a bit was this very strong jumps here in the power consumption over here. So I was already in my mind, can I find a feature that kind of explains this? Because if I can explain this, this reduces the error of my model quite a bit. Then this signal here, that seems like strange to me because it's on in the very beginning of the mission, but then almost never used again. So what I did here, I just speculated that this will not be used, and I put it on the mean of it, and it turned out to be quite okay to do that. And another thing I noticed that there's some trend in some of this in this signal. So somehow I need to incorporate the duration of the mission in there. So that's stuff you can already see from the output of that needs to be predicted. And then, yeah, these are kind of the features that I used in the first iteration. And I think most of it we really covered, like the indicators of umbra, penumbra, the height over Mars, the solar aspect angles, and some lags and moving averages on that. And on the DMOP signals, I started just with the number of commands per hour per subsystem. So that was like 17 features over there. So very basic. And then what I try to do to get new features is actually doing a cross-validation, and doing a cross-validation in a way that I can almost cover the whole period. So I trained on the first 4 years, and then tested on the last one, and then I shifted it a bit. And I left a gap in between so that I don't have this interpolation effect that you could get when you predict from the future in the past. And this is the output of this first iteration, and now you can really look at where the model is making the error. And it seems like, okay, this on the mean, this one is pretty much good. This one here, okay. It has some problems, especially when it switches from train to test. But this one, I was not really satisfied with the behavior on this signal over here. But still, I got a 0.103, which is quite good. And this was with an extra tree model. So I was already, I think, in the top 5 back then. And then I did the second iteration, and I got really obsessed with this switching of this 2551 signal, and wanted to understand why is this, and for especially why is this not happening over here? Because it seemed like every time this eclipse period ended, also this signal went down. But then this behavior stopped just in the last year of the training set, and this is also what my model then completely confused. If you look here, it goes down over here. And that was quite dissatisfying. And then, okay, so obviously it's not this one. And then we had this meetup where we actually met Luke and some of the engineers, and I asked about this problem, and they said, well, there was a change in operation, and there are basically 2 states that the system can be in from now on. And it's somewhere in the DMOP signals. So, okay, then let's hunt for it in the DMOP signals. I looked at the counts of the different subsystems, but didn't find anything that correlates to these steps. And then I thought, okay, I need to go to the individual commands and figure out where this is happening. And what I did is just plot, so like a spectrogram of the DMOP signals. So the columns, or the y-axis is the DMOP signal ordered by the name of the command, and the x-axis is time. And then I was looking for something that can explain why it's going down here, and it's not going up here, it's not going down over here, while still it's a non-eclipse period. And I was zooming in, and then at some point I found this ATTT system, which also you found with the on-off signal. And I discovered, okay, here I see a lot of commands on this one, then it switches to this command, and at the same time it goes up here. The same happens here. And then actually in the test set, there's one switch in this system that never happened before. So this command actually never showed up before. And that's really difficult to pick up for a machine learning model, to have an unknown command. So what I did is then I created one indicator feature that, where is maybe I take this one. Took an indicator feature that just covers this period where the signal goes down, and then based on this switch and this switch and this switch, I put this indicator here. And a few other things like solar conjunction, I put indicators, days since 2008 for the trend. And some periods with missing data, and just those few indicator features improved the model quite a bit. So you see that it now directly follows these steps, and also over here in the last year it follows pretty well, or even at least it doesn't go down as before. And that gave me a 0.0928. I think that was second place at that time. And now I thought, okay, enough of the feature engineering, let's do some brute force stuff. So my pipeline then overall looks like that. I have the feature extraction, then I use gradient boosting trees, which is XGBoost. And later in the competition, we discovered LSTM, or we got it to work. Like, I think Keith was using it all the time, but then during the hackathon, we got it working as well. And I also tried some simple neural nets as well, and had some method to actually select the best models to combine and then come up with the final score. And also here, the best model was a gradient boosting at 0.09, so that could be also something you could use in production with very low compute effort and also engineering effort to put it in practice. Okay, so source code is available for that as well, and just to the end, I want to show what's the difference between a recurrent neural network and the classical machine learning model. So if you would take XGBoost as an example, or regression trees, this is looking at input features like the 98 one that I had. Then it's training a model like a function that maps these features to the 33 output lines. And the problem that you have is that it doesn't take into account what happens the previous hours. And with recurrent neural net, you actually train a model that has some memory, and it can learn how to fill this memory based on the previous training data. And while it's training, it's backpropagating basically the error in time and learning how it should use the previous data to then come up with a function to map it to the final outputs. And this one, it was not better than gradient boosting, but it performed roughly the same. And when you combine the two, it makes different errors and then improved the score quite a bit. So if you look here at the different predictions from the different models, we have XGBoost, LSTM, and a 2-layer or 3-layer neural network. You see sometimes here the green one, the XGBoost is better, is closer to the signal. And at other points, where do we have it? An example. I think here the LSTM, the red one, is closer to the actual signal. And you also see in the future they're quite different. So then combining those two gave them the extra boost to get into the fourth place. I must say I would have liked to spend more time on the competition, but in the last week I was already working on another competition, and I didn't expect so much other participants putting so much effort in, so I had to stay out, unfortunately. But yeah, it was a lot of fun working on it, and also it has really a good cause. You know, I'm a data science consultant, and every day I work on stuff that has to have immediate business value, either making a customer buy more or saving money somewhere, and it's all about business. But here it had a real purpose, and that's why I also try to share all my models and the scripts early in the process so that more people get into it and there's more competition and more knowledge sharing going on, and that also worked out. Good, so I have finally some disclaimer. So I would be careful using this model in production just as it is. And I think any of those models that we have built, because especially if you want to do optimization based on those models, you need to be very careful that you don't move out of the valid range of your model. And what I've seen, and for example, for the solar eclipse, solar conjunction period, this has, most of the time it has a direct impact on the power consumption. Yeah? So the model learns, somehow there's a correlation between the environment and the power consumption. But actually the environment, it's not about the environment, it's more about how you then operate the satellite during that time, and that influences the power consumption. So if your model tells you, okay, change your mission, or if you iterate over different mission control options and then check with the model what are the predictions, you need to be careful to not go in a range where you never had previous training data. And what I would suggest to overcome this is to work with the engineers and really check, or with you also know which features make sense or not, and really just select those that really make sense. Otherwise, I think it's very risky to move out of the valid range of your models. So that's it. Thank you very much.
Thank you, Alex. You can.
The presentations are always very interesting, and during them I think, yes, I must comment on that. Oh, and that, and that. And by the end of the presentation, it's of course gone completely. So I had 3 things from your presentation, and I've only remembered one, but it applied to others. people were asking about degradation and decay, and you were saying that I think one of the lines, you saw this way at the beginning somewhere.
Yeah, I can
you saw a trend upwards.
Yeah.
And this is true. Now, whilst you can see that very nicely, because you're data people, as an engineer, what I do on my model is every Martian year I effectively kick the model and add in 5 to 10 watts and play with it until it looks about right, and then leave that for the next Martian year. So my model is really quite crude, and it does require these periodic adjustments.
Yeah. And here, I think the recurrent neural networks, they're very good at taking this up, that there's a continuous increase in that, and as long as it's kind of linear, I think it can automatically compensate for that.
Yeah. And the other one was the way that we operate the spacecraft, where you've got your step functions.
Yeah.
So yes, indeed, we make changes. As the spacecraft ages or other circumstances arise, then we have to. And just for your curiosity, so you know what it is. So, our spacecraft again. So we have MEX. Can this be seen? Anyway, this is MEX, and we have the high gain antenna at the front. On one side, we have all of the XTX, all the transmission equipment, all the communication equipment is just behind there, effectively. And the transmission system, communication system takes up a lot of power. And it gets very warm, to the point that the heater line that is behind this side switches off whenever we communicate. It's a very clear relationship. But because it takes up so much power, when we come into an eclipse season, we do not run it as we would otherwise. We run it in 2 different modes, which is, I think, as you described it. So what we can do is the communication system has various subsystems, and we can leave most of them sort of on, but not fully powered, and we're not actually communicating, or we can switch the whole system down. And during the eclipse seasons, we take the whole lot down between eclipses, and or when it's not in use. So rather than having sort of a baseline that is always powered at all times during eclipse season, we don't. We switch off the communication system completely, apart from the times when we're communicating. So this is what you see. Okay. That is line D3.
Yeah. But then here that means you didn't communicate during that time that much, so that the heater had to pick up for that.
Microphone.
Yes.
Oh yeah. So, yeah. I think, did you get it? So here, apparently it was non-eclipse period, so there was not as much communication as usual, and then the heater had to compensate for that.
Yeah. So then we have the heater compensating because we don't have the communication running at a sort of a standby level. Yes, and there are other. Truly, it is interesting to see which features you pick out. And this 22551 is the heater that is behind the communication side. And so yes. And you spoke about looking at different LCLs, different heater lines or different power lines, and then maybe looking for features for that particular power line. This would be very interesting, and it would tie in exactly with where you've got down 21, or not, down 128 and so on, and Ying was talking about warm-ups, because the bottom of the spacecraft has a particularly large heater line on it, because this is where the CPF, the fuel lines are. And so you will find there that the feature which is important here is very different to the feature that's important here or here. Yeah, so that would actually be quite an interesting thing to find out as well. See, I did remember what you'd all said. I just had to put it all together.
And just one question from my side. So this command over here, I have to look it up, but could it be that some commands were only used in the test set? I think it's 309B, ATTF.
Yeah, so ATTF 309 and 306, P and Q, are part of the communication commandings. So this would be switching it on or switching it off. There's also a period, excuse me, we do we do different types of observations, and sometimes we use the X band only for communicating. Sometimes we use the S band as well for certain observations, and this would be slightly different as well. So that's what and the periods where we do this S band communication, it's for certain specific observations that you can only do at certain phases of the orbit of the year. So yes, you'd find it just in a discrete period.
Okay, thanks.
Okay, any more questions? I have one remark, maybe. I mean, you share your feeling about this. I know that Keith Trunka, who was the guy using recurrent neural network, was first for a long period of time, and you were behind trying to. We could see that. I mean, you were evolving, trying to reach this. Then you got first, and was it like you lost the game? I mean, the game goal, like you lost the motivation to go further, or? Is it that?
Yeah, I tried a few things more, but then I was not so successful. And then, of course, if you're first, you get lazy over time. And there was also not much movement during that period. So, but that's the usual effect. And I think timing in a competition makes also a big impact, because always towards the end, people start to invest more, and when you enter too early and you get a very good score and then you are pushed down, it's very hard to remotivate yourself to get back. Whereas when you enter towards the end, you have probably more a steeper positive gradient.
Hello. So, if it's not a secret, what was the other competition about, and how did you do?
It's not as interesting as ours was. Just
course,
so you know.
Just asking.
One was a deep learning competition on the State Farm on Kaggle, so about detecting distracted drivers in a car. And the last one towards the end that distracted me was quite a useful competition, because it was about finding medical publication that fit to a patient case describing his diseases, and then out of 1 million documents, you need to find the top 100 that are relevant for diagnosis and treatment. So
I concede they're quite important and quite interesting. Right?
Okay. Dimitri?
Just a question. Do you think that the recurrent neural network can improve its efficiency if you take a smaller gap in time, like 1 minute or 15 minutes? You would have more data to train it.
Yeah. I think two things that I missed compared to the previous competitions at previous participants is having one model per line, because I always trained a model for all the outputs at the same time. So the recurrent neural network was predicting 33 lines, and also XGBoost, I kind of manipulated the data so that it becomes a single output problem. That's certainly something that could improve that. And the other thing with the on-off signals, that's another effect. And then, working on a higher resolution obviously might have also had some benefit for you. So all that could be added to this solution as well. And likewise, my stuff could be added to the other guy's solution. So I think there's plenty of room to improve or get even more accurate results after the competition and combining features and models. Yeah.
That's true. We will be working on that, and thank you, Alex.
Yeah.
We can applause. So now I was planning a little panel discussion, because you talked a lot between each other, but we have some candidates here, and I would like to call Yingu to come and sit at the table. I will also call, do we have Rafal Saikon? Okay, that's you. I was not sure. So Rafal from Fornax, codename Fornax into Space. Please have a seat as well. So you were third, actually. Yeah. And I would like to call also Jose Martinez from the Dato, Isa, and Wolfgang Steitz. Please. So, okay, of course. I wanted to get the leaderboard up. Just select this.
So, you'll have some nice and interesting experiences. I don't know if you shared that to the people, but you shared that to us, with us. And I would like to have first a round table. And I will start with Wolfgang, and present yourself and how you got to know the competition and why you did take it.
Sure. So my name is Wolfgang Steitz. I'm working as a data scientist, actually. Did a PhD before at the University of Mainz. And I started the competition actually after the meetup where we showed the spacecraft and so on. Then I became excited and I studied it. And it went quite well, but my motivation was actually to get to know some more about the machine learning models. So I wanted to try XGBoost, and well, it kind of worked.
Well, I'm Jose Martinez. I represent a bit more ESA here, so I pass the microphone to Ying.
Hello, I'm Ying Gu. I do my PhD in University Kaiserslautern and also German Research Center for Artificial Intelligence. And my major topic is about anomaly detection. This is also a part of data mining. How I know this competition is because of the meetup. I always think I'm a PhD student, but I think data mining is applying the science. So you needed to do something with the real world. So I come to the meetup and find a more interesting topic. After that, I know the competition, and it is meanwhile come to very brilliant guys come to me. One is Gagan, and the other is Pravin. They come to me and ask me a math thesis, and I think cool. Then we do this competition together. We make a team, so we do that, and that is a lot of fun. Yes.
Yeah, thank you.
Hi, my name is Rafał Saikon. I'm from the team Fornax into Space. One day I was browsing the Reddit, the machine learning subreddit, and there I saw the link to the competition. So I read through it, and I just called the guys at the company and said, look, there's a competition about saving the Mars Express orbiter. It sounds very interesting. Let's do this as a kind of a team building and to hone our data science skills and do some nice machine learning. And so we participated as a side project and had a lot of fun with it.
And of course, at the table we have Lucas, that you know.
I've spoken a lot today. You already know me as the mean one who asks difficult questions, so enough has been said.
And what I wanted to emphasize here, of course, this is a talk, so do not hesitate to stop and say what you have to say. But we've met Yinggu after the competition, and we had an interesting discussion for education because she's a PhD student, but she's supervising several students, and Gagan and their friends are here. And the thing is that we didn't know that this could be so useful for education, and also not just for the challenge time, but in the future. That's why we will release the data bit by bit, so that every year supervisors and teachers can use the data set as a school study data set somehow. So maybe you have a word about this.
Yes, so I want to say how I have the idea to do the competition. Just because beginning of my math thesis, early I was a mathematics. I studied mathematics in University Heidelberg, but in my math thesis I got a competition topic that's about 2007. The Netflix data set, it's a prediction for the user preference. So at that time it's 2012, and the competition is in 2007. Everything is gone. I'm just alone, do the competition alone, and I don't know the solution from the others. I'm very happy with my result, and I think the topic is very interesting, but no one else interested in this topic because this competition is already ended. I'm alone in this topic. So a little sad. After my math thesis, I find I really like data scientists, so I go to German research center for my professor. I asked him I want to do PhD in data science, so he told me okay, and I needed to also supervise some students. So it's cool at this time. Gagan and Pravin come to me, and I think it's a good chance to do a competition together, because in this competition there are so many people do the same topic and have fun with that. And I think in all the experience, all the time here, the most important things in the data scientist is you need to have fun. How you can find fun? You need to have the friends, they do the same thing, and you need to do some real world topic and not just learn something from book. Because if you just learn something from lectures, you will sleep. Because in the lecture, every data you got is very clear. For example, the iris data set. It is so clear data set. You don't need to think anything, just apply the algorithm, it works. But in the real world, it is others than the iris data set. You need to do many data pre-processing. You need to think a lot, so that's the fun in data scientist. So I think this is my experience. So after that, I also find Gagan and Pravin, they have also fun in their math thesis. Yes, I think it's great.
Yeah, so that's what guides us somehow. So, yeah, Luke?
If I add, so you came to see us and you discussed the effect of the challenge. And I'm glad, I'm thrilled, right? And to see you all motivated, but you said you'd managed to get your students to come in on a Sunday to work on a problem, and the guys who were doing stuff on night shift and on holiday. Students are great and we learn lots. I've done my time there as well, but getting us to work on a Sunday just for fun and actually calling up the professor to say, will you come in and support us on a Sunday is almost unheard of. So I'm glad for this result.
Maybe we have another kind of experience with you, Wolfgang, or yeah. Well, whatever. I mean, how did it change your life?
Well, for me, it was a bit like, in the beginning, I did all the feature engineering more or less at once. So I downloaded the data, kind of made my data set, put it all on hourly level, extracted some, and then just played with machine learning models. So I never used XGBoost before, so it was more like testing how it works, find out how to train it and so on. And I always wanted to use it, trying to find a use case in work. So now I used the competition to learn how it works, and now I have a problem actually at work where I will apply this. So it definitely helped me to learn more about these models, and also to exchange at the meetups and at the hackathon that we had with the other participants to learn about those models. So for me, it was a very good thing to learn. So I learned a lot about models and how to do it.
Yeah, actually the leaderboard is only the top of the iceberg, so there's a lot of knowledge sharing. There was a lot of knowledge sharing during this competition, and also some method shifting in how you do things every day. And I think Rafał Steichen, you have something to talk about. So Rafał, you're CEO of CTO of Phonax.
Yeah.
So this is a startup.
Yeah, pretty much yes. Yeah. I mean, we are slowly moving into the position of being a small data science and machine learning consultancy company, and we are from Poland. And there's a meme like it's called the Poland Ball. Maybe someone you heard about it. There's a story that Poland cannot into space. So we named our team Phonax, Fornax into space, because this was our dream to climb high here. During the competition, it was very, very exciting, and we put a lot of effort into it, even though it was a side project. For the last 2 weeks, I believe, we even managed to be on the top of the leaderboard. But in the last 2 days, we were jumped over by, I think it was Red Rock at first, and then the Slovenia team. But still, we are pretty satisfied with the result. And from the competition, we learned a lot about how to manage the team, because in the stressful environment where a lot of tasks were being done, we learned a lot from the competition. And we also spent a lot of time honing our data science skills, reading up on the models and doing lots of analysis, which was very, very insightful.
So this competition was the opportunity to try something new with the teams?
Yeah, exactly. I have learned to because previously when I was managing the team, I was trying to have a lot of control in what people are doing, and I was assigning tasks and so on and supervising it. And through this competition, I have learned that it's very, very important to give a lot of freedom and a lot of responsibility to people for their tasks. They are becoming more and more involved into what they are doing, and they are coming up with a lot of interesting observations on their own, and they are willing to spend a lot of time working with it by themselves, which was great. Now we are applying the strategy to every new project, and it's working beautifully. It's a great cooperation that we learned through this competition.
Yeah. And we were very happy to hear about this. So thank you for participating, and we are very glad that it helped you team building somehow.
So thank you very much.
Yeah, you're welcome. And maybe Jose, you can talk about what we're going to do there.
Yeah. So I have to say that we also learn a lot from this competition. So we gave you some data, and we didn't have any expectation in the sense that we didn't know how possible this would be. I mean, we knew there was some meat on the data, but we didn't know how far you can get. And seeing the results, you can see that was excellent results. So the plan we want to go is, of course, use it. We were discussing yesterday with Luke on how useful or how much data we need for this to be useful. Something we notice also is that the prediction models work better the closer they are to the time they were trained on. And for us, still useful if we just need to predict in the next 3-4 months. So I guess that we focus on the 3-4 months and then retrain models in this kind of period, we can get even better results. So this is what we're aiming at.
Yeah. Also, I think we have provided a context which is not all the context, because you have a lot of what's happening on a spacecraft, but not much of what's happening in space and could infer changes in the spacecraft. You have indirectly the albedo of Mars, because you have the distance to Mars that you could compute. You have the solar constant, for instance, but you don't have the solar weather. And by looking at your predictions, I was trying to see if we had a link between the prediction error and some space weather events. And it appeared that on some current lines, we had those problems, meaning that you had a high error when you had a solar event. So we have to investigate, because not all the lines are constant, because only those facing the sun somehow. So maybe in the future we'll run this competition in a more enriched, with a more enriched context. And I think that's the follow-up of this direct competition, I would say. But the follow-up for us is really building those intelligent systems for operation. And this is just a step. So we are discussing what we could do next. And also, thanks to this competition, we had a lot of connection. So Wolfgang Weicht, we discussed that very quickly at lunch, but maybe you can have the mic. But I would say that it took a lot of time to reach out. So we didn't have much time to do the baseline, for instance, so that would have been fun. And neither a starter kit like you provided. So what we would love to is to hand with you, try to do the following competitions with you, hackathons, competitions, whatever that could be, but trying to, with your help, trying to reach out more people and have like more, I would say, manufactured challenges, because we could take more time in preparing the data and doing more material at the beginning. So in that sense, we need budget, of course, so we're discussing internally. We have different things happening internally. But if you have any sponsors, or if we can outsource the organization of those things, that would be a great deal. Yeah, you can. Yep.
One comment before Sandro, I think, rounds up, is that there may be, for some of you, questions that are still outstanding about what you've seen. For instance, the NPWD 2551, which I've now explained, and now hopefully you'll say, aha. So this is why you see what you see. If you have other questions that are similar to that, then do get in touch. I will endeavour to answer. I mean, some of them are going to be repetitive, and things that you've seen are, I mean, if you've seen NPWD 2551, so have many other people as well. So if you have questions that are still burning about why did I see this, or why didn't that work, or why was this period different, let me know. I'm going to be around outside anyway, and I'll see what I can do to answer them.
Well, I just want to say one word of conclusion. First of all, thank you so much for the interest and the enthusiasm and the pleasure that you show using your competence to participate in this challenge. What we have done today, I would say, is we reinforce a bridge that was already existing, but now is much stronger, bridge of trust between data science community and mission control at ESOC. So I think this will pave the way in the future to look at the capability not only of internal activities, but also with the cooperation with the data science community on future challenges, and make let's say, the activities and the operations more, exploring more the capability that data science can provide to mission control. So we are also interested to your ideas and exchange of ideas. From our side, we will have more brainstorming in-house across flight control engineers, flight control teams, on what could be solved and or challenged. And then if something comes out, you will see. Stay tuned. Thank you so much. Now it's time for the coffee, and we have also some other pastry for you guys.
I have just one last thing. I have the mic here. It's something we could not really do because, we'll have two last things. So please, Luke, I'll start with mine. And that was for the winners. So I'll use the camera here because it's quite useful. My camera. This one. Not like this. Okay. Okay. Somebody help.
I think the one who's speaking always gets in front.
Yeah. Should I speak then? Like this. I'm the master now. Now? Okay, whatever. So, we wanted to, maybe you don't see it here. Well, oh, maybe. What is this?
Yeah, cool.
So, we wanted to print in 3D, so 3D printing, the absolute error of the winning team. So, unfortunately, that's why I was late at the dinner, because the 3D printing got jammed yesterday by the LibreCube project. They are printing CubeSats. This is here you have 0, so it's good. And unfortunately, on this model you don't have the scale, but it goes until 7. But it's quite close to 0, all things. So here you have 3 somewhere here, so it's quite good. 3 amperes, of course. And so I will hand this to you because this was meant for you. So it is a Mars Express Power Challenge, but we missed some centimeters there. So this is for you.
So that is very cool, and what I've got is not nearly as cool, but it occurred to me, there we go, that for your institute you might want something else. I mean, you guys will be wandering around with the great, and you've got this, which will go in an office somewhere or behind like on the mantelpiece. But in institute, you probably want something as some kind of a record that you've won, yes? A certificate of sorts, we reckoned, and of course we only remembered this at lunchtime today. The jackets we've ordered like weeks ago. But we do have a certificate, just Red and I have signed it. It is a nice picture of our spacecraft. This is MEX, and this is what you've done for us, so thank you very much.
Yeah, so one last announcement. Now we have coffee, so we can have some time to discuss with each other. And after this, we thought it would be a good idea to continue in the browse tool, where we can have some beers. So we reserved some place there. If you happen to be willing to join for a beer with us, then we go together. Sorry?
I mean, you can go with Jose, but if you're vaguely familiar with the area, it's directly opposite the train station. So if you came here by train today, it is just opposite, just so you know where you're heading.
Yeah, if there is a cinema.
Yeah, there's a great big cinema,
so it's
and to
next
the
door
side,
to the cinema.
a good German pub.
Follow the winners, they know it.
So thank you, everyone.
Thank you.
There are also some posters you can have till they are gone.
Have enough for everybody? Yeah, Malcolm. Yeah. Dimitri. I guess we have somebody who's coming from really far, who's coming from more than 1,000 kilometers from here. Yeah, Leo Tam. Where are you coming from?
Excuse me.
San Francisco Bay. He works at NVIDIA. We have Poland.
Unfortunately
Switzerland.
not. I mean, they were not the
We have
easiest
Darmstadt
to
as
get.
well.
It took some effort, and then when I had the team of 7, we got 7, and then because I'm not as hard as I always appear, because the second guide was one person, I thought, well, but unfortunately no, this was all that we got from.
Thank you really for organising all of this. I mean,
Red did most of the organisation. It was, I mean, at the beginning. That was, and which they could use and which not. There is a lot more data on the space part than we gave to you. We had to sort of try and figure out what to give and what not. I'm not sure. People were discussing about whether sometimes it's more broad, yes, sometimes take more some of the stuff since 2005. But because part of the point was that I see things from my perspective and as an engineer and knowing spacecraft, and the idea was to give it out to a completely different audience and see how they attack it. Exactly. So there wasn't anything unusual, like take some like that, like give them everything and let them look at it in whichever way they look at it and come back and see what it comes out.
if you combine your expert knowledge plus...
It's really quite fun to see what people picked out. it's like, no, that's true. That line was a lot, and it's because it's on the site. One of the guys was saying that one of the lines needs to be always on. And yes, I don't know the parameter, but I know which line it is, and this is true. Or they found things with it, that they called it down one or down something like this. We found called it warm up. Yes, it's the same thing. And yes, it's true. What's more, because warm ups we do, yes, formally, and I have an idea, I have a notion, I have a 3D set that they help. But every warm up we do is slightly different. Yes, and then the second set is slightly different. So being able to quantify it and say yes, it definitely does, has been incredibly difficult, because I can't. I don't have two circumstances where I can compare line with line. So the fact that I give the data out to August and 3 groups come up and say, by the way, this. So I can't quantify it, but I know that it helps. I know that it helps. So yeah, it's been, and to see that it's so enthusiastically received.
Space related, but because he knows that like you're going to help the mission, so that's what motivated me.
But it does, and part of it came up because next year we have this horrific year, the period where we have upheaval in the sun, and we have eclipses and a lot. Some eclipses, the eclipse itself is only 30-40 minutes. Next year they're going to be 50-something minutes. So this is a long eclipse as well, and it's perfect. Yeah, so we've been doing other things in this lesson, we actually test out strategies on the it's actually when the next one, I recommend going because it's not like there's I guess I'm not going to have people here, but this is also another good point you think and look and act in a different way. Yes, you consider things and know a lot more in their field. It's utterly inspiring. It's really, really great. So yes, I recommend it.
Do you newsletter or some sort of thing that finding the information on you is quite can go down a little bit. Sometimes I think that find that a bit difficult to navigate sometimes.
Masters Press has a blog. However, it's only updated periodically. Sometimes the astronauts have a team who blog for them. Yeah. We are a team that have our full-time responsibility to do, and occasionally when we get a chance, we don't blog very often. But if there's something new or different, so I blogged about this last week, this is what's happening. When we had a comet in Kansas, we had lots of blogs then. And the VMC video that I showed you was when we had created the use the camera for schools to contact. So we did a lot of getting schools and people in.
And there was one thing I wanted to ask, it's not related to this, but related to Rosetta and Philae.
Yeah.
So all the operations were done here?
Yes. For Rosetta, Philae has its own operational centre from, where are they? Are they in Cologne? No.
Cologne.
Thank you very much. They're up in Cologne. And so once we dropped Philae, then it was operated from Cologne. Yeah, but we did all the stuff with Rosetta.
Because I'm from Italy, so